Okay, welcome to our second session. We had a really good showing in the first session. I think well over 50 people and a bunch of good talks. The first session is currently being uploaded to YouTube, so if you missed it and if you're interested in any of the talks, you will be able to watch them pretty soon. Okay, so before we begin, I would like us to do a round of introductions like we always do at the beginning. And now we have some new people. And there aren't that many of us, so it would be good if we all just go around and introduce ourselves one by one. And I suggest we do that by you just kind of raise your hand in Zoom, and then you're going to show up on my list. And if you don't know how to do that, just at the bottom, there is a react button, which is a little heart. And if you click on that, it says raise hand. So I'm going to start. I'm Dennis Vida. I'm a professor here at the University of Western Ontario, and I like meteors. So up next, we have Gene Ross. Gene, go ahead.
My name is Gene Mraz, and I'm in Santa Fe, New Mexico, with the New Mexico Meteor Array, and I'll be talking in about an hour about some recent investigations into how we might use RMS to understand light pollution.
Thank you, Steve. Marshall, go ahead.
Yeah, g'day. I'm a geologist at the University of Otago in New Zealand, and I've also been sort of helped set up our network here and help with the searches for the meteorite and that sort of thing. So yeah, g'day.
Awesome. Thanks, Marshall. And yeah, I see Steve. Steve has his hand up on the video. So Steve, go ahead.
Yeah, hi, I'm Steve. I've had a camera for just under a year. I got a little bit involved in writing some software, so you've probably seen that for Status Viewer. Um, I guess I don't have an academic background. I got an engineering degree 40 years ago, and I've been working commercial since then. So this is all very interesting, and sort of it's good to be involved.
Thank you, Steve. Next up, we have Derek. Derek, go ahead.
So I'm from Victoria in Australia. I've been part of the Meteor Network probably about 3 years, retired scientist. I've sort of ended up coordinating the camera installations in Victoria. We've got about 12 up now, sort of right across the state. And we've got two DFN cameras, which we'll talk about later on this morning. So, yeah, all good.
Awesome. Thank you. And Jamie. Jamie, go ahead.
Hi, I'm Jamie Shepherd from Scotland. I operate some cameras up here. I'm a meteor nut since I was a boy, and for my lifelong, I've been an analysis nut. I just love crunching the numbers on these guys. And welcome, good to meet you, all the guys down under. Good eye.
Thank you. Thank you, Jamie. Okay, Sam, go ahead.
Hi everyone, my name is Sam Himmelgarn. I'm a first year PhD student at Northern Arizona University in Flagstaff, Arizona. I got involved with the GMN through LOCAMs, Lowell Observatory cameras for all sky meteor surveillance. It's an array of 8 meteor cameras here in Arizona, and just found it very interesting and fun to work with the data as well.
Thank you, Sam. Paul Rogermans, go ahead.
Hello, I am Paul Rogemans. I live in Belgium and I have meteor cameras in several parts of Belgium and the north of France. Um, I am involved with meteors for more than 50 years now, and since I'm retired since 2023, I hope to have more time in meteors, but so far, getting older, I get less done than I would like to do.
Good. Thank you. Thank you, Paul. Is there anyone else who would like to quickly introduce themselves? Pete Ashman, go ahead.
Yeah, I'm here in Albuquerque, New Mexico, and I've been serving as area coordinator for the New Mexico Meteor Array for a number of years now. Gene is one of our major contributors, and hopefully there'll be a few others in our group that are going to tune in as the session goes on.
Thank you, Pete. And then Alex, go ahead.
Oh, hello, Dennis. Hi, everyone. I'm really happy to be here, and I'm able to do a talk over here. I'm actually trying to build an app for GMN because I want to make this a simple machine like this a meteor camera. So currently it is looking good, and my app is set to be available at the end of this month. Around the end of this month, I'm going to do a talk about it very soon. So stay tuned. Thank you.
Thank you, Alex. Next up, Steve Wynn Harris.
Hello, I'm here on the east coast of the North Island. In fact, nice shot of the sea out there if you can see it. And I, along with Marshall, we found Takapua, which he'll talk about a little later, back in March. So enthusiastic member of Fireballs Aotearoa.
Thank you, Steve. Okay, so who do we have next? We still have a few more minutes. You can feel free to raise your hand or just speak up. Bob, go ahead.
Yeah. I operate 3 cameras here in the south of New Zealand, South Island, and I think I'm supposed to be responsible for a few others, but the technical side of things is I'm still learning very slowly, but catching quite a few meteors though.
Thank you. And let's see. Is there anyone else who'd like to say a few words about themselves that we didn't have yet? How about Luke, if he's around?
Hey, I'm Luke from Phoenix, Arizona. I'm an airline pilot interested into reducing the climate impact of aviation, and I did a talk in the first session this morning.
Thank you, Luke. Yeah, so definitely check out Luke's talk about GMN observations of contrails and the fact that we have a chance to shave off about 2% of climate change impacts. Okay, let's see. Is there anyone else who'd like to quickly introduce themselves? Elizabeth, go ahead.
Hi again. For those of you who were not at the morning session, morning for me at least, my name is Elizabeth Silber. I'm a senior research scientist at Sandia National Labs, and I'm also affiliated with Western University, and I collaborate quite a lot with Western University. My specialty is meteor infrasound and meteor shock physics.
Thank you, Elizabeth. Okay, and pretty much my last call for some more introductions. If anyone would like to quickly say something about themselves, but I think we've been through, I think pretty much almost everyone said something. So we can go to the next item, and that is the recap of session 1. So that's something that I usually do for our friends in Asia, Australia, and down under, so they don't have to rewatch the whole, I don't know, 4 or 5 hours of the first section. So I'm just going to give you a very quick overview, and there are some people here who gave talks in that first session, so I might ask them to just say a few words about their talk, because they know better than I do. So what I'm going to do is actually pull up the recording of the first talk, so I can sort of the first session. So I can actually show you, just share my screen, and then how about this? I'm just going to very quickly go through the individual slides and talks. So the first talk that we had was by Professor Paul Wiegert, who works here with me at the department, and he looked into finding interstellar meteors in the GMN data set. In the GMN, we have almost 2 million meteor orbits, and the question was, are there any possible interstellars in the data set? And unfortunately, the answer is no. We didn't find any that are conclusively interstellar. Now, of course, if you blindly go in and look at the eccentricities of the orbits, you will find interstellars in there. But when you actually, scratch under the surface, when you do the manual reduction of meteors, you will find that unfortunately, they end up being on bound orbits. So most of them have one error or the other. Sometimes the wrong meteor is being associated, or it's involved in a cloud, or the velocity is ever so slightly incorrectly computed. But one thing that we are able to do is to constrain the flux of interstellar particles that come into the Earth's atmosphere. So what you're seeing on this graph is on the x-axis is the mass of interstellar particles. And the only real measurements that we have are on the left-hand side. So there are some very, very, very small dust particles that have been measured on spacecraft to have interstellar speeds. So these are the real particles. You can see the flux, basically the number of these particles and their mass, and they're tiny, tiny, tiny. On the other side, you have Oumuamua and Comet's Borisov. And of course, you can compute the flux this way. And then you could potentially connect these dots with some sort of a line if you are brave enough across 20, 30 orders of magnitude of mass. But the truth is, there are no measurements in between. And well, there are some measurements, but these are mostly upper limits that have been set. And there's some measurements that people don't usually tend to trust. So what the GMN is able to do is put a point down here and say, well, we haven't detected anything yet. But because our collecting area is so big, because we have a meteor network around the globe, we can push this limit all the way down, and we're starting to approach this theoretical model. So it might take a few more years of, not seeing anything until we should start seeing one or two interstellar meteors into GMN statistically. If we don't, then either something's wrong with our data collection or something's wrong with our theoretical models. Okay, so the next talk was about our friends from Tajikistan. They are located in a very strategic point in Central Asia where there aren't any meteor cameras. So if there was a meteor shower outburst to happen over Central Asia, they are going to be the ones that are going to record it. They have a very rich history of meteor research. And their funding has taken somewhat of a downturn in the post-Soviet era, and then the GMN stepped in and donated two GMN cameras that they're operating and contributing to our mission. And after that, we had a talk that is about the Geminid meteor shower. So, a bit of context here. The Geminids are one of the strongest meteor showers. Their parent body is known as the Comet Phaeton, and they're extremely mysterious because it's a big meteor shower, and the asteroid is silent. It produces very little activity. So, how come you could have this giant meteor shower and yet an asteroid that shows no activity? People have tried modeling it with some sort of a big impact or some sort of a fragmentation event unsuccessfully. So what these scientists did is they ran simulations of Geminid orbits as observed by the GMN, and they computed a median value. And they, of course, developed some new mathematical methods, but I'm going to skip that part. But what they found is that they see a convergence in the orbits when you go back a few millennia. And from our direct GMN measurements, they estimate the age of the Gemini meteor shower to be about between 1500 and 2000 years, which is roughly in accordance to some previous numerical models. So it was nice to see that the GMN can help the GMN observations can help inform these modelings and answer the mystery of the Geminids. Hopefully one day. And next up, we had Elizabeth. So Elizabeth, would you mind in a minute or two quickly summarize your talk?
Oh, yeah, sure. Thank you so much. That's convenient. So we have observed an Earth grazer, which is quite a rare event, horizon to horizon fireball. This horizon to horizon fireball also produced infrasound, which is low frequency sound below human hearing range of 20 hertz. Benefits of infrasound is that it can travel over long distances and it can give us some information about the characteristics of the object we are observing. So what's very unusual about this, or rare about this fireball, was the fact that we observed the infrasound from 90 kilometers altitude. And the really, really cool thing is that we detected signals at 3 infrasound stations, and these signals came from 3 different parts of the trail. This was enabled by very high resolution optical observations, and I thank my collaborators and the entire team who had been involved in capturing this amazing video data. And from this, we were able to obtain mass and size of the object.
Amazing. Thank you, Elizabeth. Yeah, short comment is that we're working on a paper together, and hopefully we're going to be able to submit it soon. Okay, thank you. And then next up, we had Dario Zubovic. So Dario was actually the initiator of the RMS software library about 10 years ago. He wrote some of the first code. You can, if you dig through the history on GitHub, you can see that his commits were the first ones, and he developed this initial idea of how meteors should be captured, and they should go into there's different parts of the software. So he gave an overview of how the software pipeline works. So for anyone who's interested in software and the details of the mechanical details of how things work, you definitely want to check out his paper. And I think this is a very interesting graph that we didn't really dwell much on the first part of the meeting, but you can see the amount of code that was contributed over the years. So you can see the first commits happened somewhere in 2015, and there was a bit of a downturn in 2017-ish or so, and then things picked up in 2018, and they've stayed strong since then. Lots and lots of work and hours were put into the code base. Okay. Next up, we had Damir who told us about photometry of stars using GMN cameras. And the idea here is, can we track variable stars using GMN data? So Damir described his method, and what he did is differential photometry. So what you do is you pick your star of interest, and you pick 2 reference stars or more, and you assume that their brightness doesn't change, and you pick something that's pretty close to avoid any other observational effects. And based on these 2 references, then you investigate the brightness of the star of interest. And then he found that, yes, in fact, after some corrections, you can get very accurate observations of variable stars. And I think this is Delta Cephei here. And the green dots here are from the AAVSO website, which is the organization that collects observations of variable stars. So hopefully at some point in the future, we'll be able to develop an automated system that can do this for all stars that GMN cameras observe and contribute to variable star research. And then we had Jamie. Jamie, would you mind telling us very briefly what your paper was all about? Your talk was all about. If Jamie is here, of course.
Yes, I'm. Hello. I can just share my screen.
Absolutely, go ahead. There we go.
There we go. Pick this one. Usually takes a few seconds for it to actually appear. There we go. Yeah, so this is the main kernel of it. I was looking at things that cause curvature in meteor trajectories and ways that we can correct for that. Now, here's a particular result which showed a strong curvature at the end. Now, we're using the same method to correct these as we used to correct for gravity, except looking for wind perturbation effects, we're just adding horizontal vectors instead of vertical vectors. And if it'll only nudge forward, I'll just use the mouse. There we go. So we started adding 50 meters per second, which is a value inspired by the polar vortex. which blows over Britain all winter long. That's the kind of wind speed you get. So we found that it wasn't really doing very much. So we bumped it up to 100 meters per second. Still not enough. Bumped it up to 200 meters per second, then 300. And we were getting quite a good fit to the data at last. But the trouble is, the polar vortex, the strongest upper stratosphere winds only blow about 70 meters per second. So that's just not fast enough. Felt a bit dejected when we got to that point. And then I suddenly realized the important thing, which is that we do have something moving at 300 meters per second, and that's the frame of reference. So the inertial frame of reference, we do all the calculations in. The green arrows are the fixed relative to the stars. And when your fireball plunges into the atmosphere, in that frame of reference, it's meeting a rotating Earth, which is speeding along pretty darn fast. So on that basis, we're able to add the two vectors together, the upper atmosphere wind vector and the frame of reference, if you like to call it wind vector, because it's meeting a sideways blast of air. And we're able to integrate that into the WMPL solver to improve the endpoints of trajectories of fireballs that penetrated deep into the atmosphere. And we did this comparison for the fireball last May over Staffordshire, which a meteorite hunt was carried out for unsuccessfully. And if you do the correction, you can see how the endpoint is bunched up in a tight grouping. This correction really seems to be effective in tightening up the fit of those vital endpoints of trajectories. So that was about it. I also looked at refraction parallax, but if you want to find out about that, well, play back the talk. Thank you.
Amazing, Jamie. Thank you for the summary. Okay, so let me share my screen again, and I'm gonna skip forward here. Look at all this amazing math that Jamie developed here. So make sure to hear more about it. Okay, so the next talk was by Teddy Carrera, who talked about 2022 WJ1. So that was a fireball that occurred, I think, directly over my head about 2 years ago. Unfortunately, I was fast asleep, and it dropped meteorites into Lake Ontario that were not recovered. However, for the first time, we were able to observe a fireball in the atmosphere and have it observed prior to impact. Telescopically, we were able to do some characterization and find that, yes, in fact, our in-atmosphere measurements are showing that it's rocky, and the telescopic measurements also show that it's rocky. So we wrote a beautiful paper about it, which got published. As I said, most of the meteorites ended up in Lake Ontario. Some of them are in Canadian vineyards, and this was the smallest ever characterized asteroid, which was the size of, I guess, like a beach balloon. That would be an accurate way to describe it. And this next talk after that, um, Mark McIntyre told us something about speeding up the GMN pipeline. However, Mark is going to tell us or give a summary of this talk at the end of my summary. So we're going to leave that for later. That's also something very exciting. And then we had Dino, who told us about the improvements of the GMN detection filtering algorithm. As some of you know, it does a good job of rejecting clouds and planes. It does a terrible job of rejecting bugs. So Dino is retraining this machine learning algorithm and making big improvements, and he did achieve quite a good increase in in the algorithmic accuracy with his scores. The old accuracy was about 0.88%, and with the new algorithm is about 0.97%. Sorry, 0.97. I guess it's 88% versus 97.4%. So hopefully we're going to see those changes implemented in the RMS code soon. He also worked on an algorithm to automatically detect sprites. the upper atmospheric lightning. But I think that is still work in progress. But if you're interested in any of this, feel free to watch this full talk and reach out to him if you want to test his code. He also developed a little app where you can monitor the status of your camera stations and get an alert if something goes wrong. And I think Alex is doing something similar. So maybe Alex, you can reach out to Dino and talk to him about his little app. Okay, so next up we had Logan Cordonier from the Air Force Research Lab in New Mexico, who talked about the observing meteor afterglows in the radio spectrum. This is a completely new field of science because they were only discovered back in 2014, and he's just doing some basic work to connect them to persistent trains of meteors based on GMN trajectories. And he had a very tantalizing proposition that to better improve his research, what he would need is a subnetwork of GMN cameras around his instrument, which would be characterizing trajectories in almost real time. So they can point their instruments to that particular location and make measurements of the radio afterglow and of the spectrum of the persistent trains. Sorry, I apologize. My voice gave out. Okay. Next up, we had Oriana Gall. She told us something about modeling the Draconid meteor shower. The Draconids are dangerous from the perspective of impacts on spacecraft because they're slow, and slow showers paradoxically have a higher impact on the modeling and the risk. And the problem with the Draconids, and she had a really beautiful graph here, that they're extremely hard to predict. So if you look at apparitions in different years, the years are on the left-hand side of the table. And if you see if they're expected, if the time of the outburst was accurate and the accurate activity rate, you can see that they failed most of the time. And then the one in 2011 was actually predicted, well observed, and everyone was super happy. And then the next year, in 2012, there was a giant outburst that no one predicted. No one predicted. So she worked on an improved model. She produced better results that fit all of the previous results. And then yet we had an outburst in 2024 that the GMN observed, well characterized, and yet that model failed to failed to reproduce any results. So there's still a lot work to be done, more observations to make, and that's something that the GMN is contributing to. And after that, we had Luke. And for the sake of time, I'm just going to say that Luke is doing incredible work in improving RMS code and writing new modules and a whole pipeline to detect aircraft contrails on GMN data. And that's something we can discuss later because that is one of the most important things that I feel that I've ever done in my life. Meteors are all fine and dandy, and we do help we do have a spacecraft, but this is something that is of great interest, not just to science, but also big organizations such as Eurocontrol that controls all air traffic over Europe. The European Union has actually given European airlines mandate to do something about contrails. And Google and Breakthrough Energy and a few other people are very interested in this work. Okay. And sorry about that. Next up, we had Pete Eschman briefly summarize how to set up a camera, a multi-camera setup on a PC. Maybe Pete can tell us something more about that in our discussion period. I'm sure that many people are interested how to run multiple cameras on their systems. And after that, we had a long period of discussion, mostly technical, but I see that our time is up, and uh, I'm gonna have Mark summarize his upgrades to the GMN software pipeline, if Mark is here. Oh, yeah, I see that he's here. And then we can have a very brief discussion of why that is important and why we want to decentralize the GMN orbit processing globally in this time of global instability. Mark, go ahead.
Yeah, okay. So hopefully you can all hear me and see my slides, but I've only got 5 minutes, so I'm going to whiz through this. The problem that we're obviously trying to solve here is that the GMN pipeline that is generating the trajectories and the orbits is running more and more slowly because of the volume of data. And last year during the process, it was running kind of weeks late. And so what we wanted to do was speed that up. And the way that we approach that is to break it up into parallel and distributed processing mode. And that sounds quite complex, but I'll explain a bit more about that in a moment. The advantage of doing it this way is it lets us essentially do the initial calculations much more quickly. They're 8 to 10 times faster than we were doing before. And then we can refine those results later. And that actually works for us because many of the consumers of the GMN data are primarily interested in, the flux. They're interested in the quick results of how many meteors did we see, what showers were they in, what were their basic characteristics. And the full detailed analysis isn't always required quickly. By taking this approach, we've also been able to start working toward a more distributed processing model. So at the moment, the pipeline is really based on one server running in the university. And the goal of this is to distribute the load a little bit more globally so that we won't have that single point of failure, won't have that single dependency on the server in UWO. I've only got a few minutes to talk about this, so I won't go into too much detail, but essentially you can think of the way the solver works as having two key steps. The first of which is to find candidates, where it looks back over the last 6 days, and it then takes each day one at a time, each 24-hour period one at a time. It finds all of the detections in that period, and it groups them up according to whether there are potential observations of the same meteor, so same field of view, same time, a few other things that it does to make some sort of sanity checks. And then once it's got those candidates, it then processes those to calculate trajectories and orbits. That first stage can take 3 hours with a heavy workload. The second stage can take as much as 8 days, and that's really driven by data volumes. Like I said, there was like between 10,000 and 200,000 observations per 24-hour period that are being processed. And so the thing we tackled first was that second stage, that 8-day processing window. Now, as I said, what's happening is we're going through all the data and we're grouping up the potential candidate observations that look like they're observations of the same meteor. So imagine each of the little squares in this block is one candidate. The original solver went through them one by one in sequence, working out the solutions. And so it's taken quite a long time. And there's 2 steps to that. There's a simple solution and there's a Monte Carlo stage that adds the uncertainties and refines the data. But of course, we don't actually need to wait for the whole thing to be done. And because of the data volumes, 30,000 candidates or something like that, this just can take an extremely long time. But those 2 stages, the first stage only takes a few seconds. The second stage takes 10 to 15 seconds, depending on how much data there is to process and the complexity of the solution and that kind of thing. And so you've got a picture a bit like the one at the top here. You've got some simple solutions, and then a Monte Carlo, then the next simple solution, then the next Monte Carlo, very linear. And so what we did was we split that into 2 steps. We do all the simple solutions in one step, and then in parallel, we do all the Monte Carlos. And that allows us to get those simple solutions 8 to 10 times more rapidly, and with typically within a few hours. And that's sufficient for updating the website with the results that people need to be able to do the basic analysis that a lot of the consumers need. And even the Monte Carlo stage is faster because it's not waiting for all those simple solutions. The Monte Carlo stage can be quite variable in how long it takes for each solution, depending upon the complexity of the data. The other advantage of this is that we're now, because we're doing those simple solutions and we're saving them straight away, we don't need to just run one Monte Carlo simulator. We can run 2 on different computers. And those computers do not need to be within the university network. There's some security matters that we've got to work our way through there before we can properly distribute this. But it gives us the ability to distribute that workload and therefore actually to bring down the times even further. You can imagine that we could run nodes in different time zones which process the data in those time zones more effectively. So this is something that we're working on. We're not there yet, but it's in flight, and I hope we'll have something fairly soon. So going back again, the original solver, very linear kind of a process, very slow. The new solver, much quicker, still takes about 30 minutes to 3 hours for that fine candidate stage, and that's something else we want to look at. But the second stage is typically running it under 6 hours now, which is a significant improvement. And on that fine candidate stage, again, that's also quite linear at the moment. We've got thousands of candidates being found. And at the moment, we're waiting until all of those candidates have been found before we start the next stage. But what we're looking at as well is whether we could actually start doing something sooner. So if we save those candidates to disk, could we then pick those up and start running the simple solution straight away? It's not entirely as simple as that because there's some other stuff going on in the background around making sure we don't reprocess the same data twice. But the principle of what we're talking about there could be done. And so those are the things we're working on. We've already made some significant improvements in the performance of the pipeline. What we're looking at should allow us to spread the load across multiple servers globally. There's further improvements we're looking at to further improve that. And the end goal really is to reduce the dependence on a single server. So we'd be processing data globally as well as collecting it globally. And that would make the system more robust, particularly as Dennis says, these times of instability. So watch this space. More to come.
Amazing, Mark. Thank you so much. We can discuss some of the details at our discussion at the end. But now is the time for our first official talk, and that's Sam Hamelgarn. So Sam, go ahead.
Let me just get my PowerPoint pulled up here.
Sounds good. I can see your screen, and I can see you, and I can hear you, so you're good.
There we go. All right. Hello, everyone. My name is Sam Himmelgarn. I'm a first-year PhD student at Northern Arizona University in Flagstaff, Arizona. And I'm going to talk to you about a project I started last semester in one of my computer science classes, applying machine learning algorithms to GMN data. And the talk I've titled Classifying Meteors with Machine Learning. So the way we currently classify meteors is with this parameter called KB. So the equation for KB is up at the top there. And basically what it is it's based on a theoretical ablation model that classifies meteoroids based on strength. And it's a function of the meteoroid's beginning atmospheric density, its initial velocity, and its zenith angle. And then in the table here, I've put all of the groupings for the value that KB can take based off of this equation. And if you go from the top of that table to the bottom, you start at stronger, denser asteroidal meteors in group A, and then group D goes all the way down to the softer, fluffier cometary meteors. So for the purpose of this project, I needed to develop some labels for my data set, and I decided to use this classification scheme that I found in the Joyrett and Koshny paper from 2023. And they basically said in their methods, they used KB of greater than 7.3 as an asteroidal meteor. And then they labeled meteors with KB less than 7.3 as cometary meteors. So the main question that we're trying to answer here is, can we develop a new model for classified meteors based on their observed properties using machine learning? KB was developed in the late 50s and 60s, and in the past 15 years or so, we have all of these elaborate meteor networks, such as the GMN, producing pretty precise orbits on meteors that are entering the atmosphere. Along with that, we've got the proliferation of artificial intelligence and machine learning. So we want to see if we can develop a newer model based off of modern techniques. So the data set that I'm working with right now is a 2023 data set from the Croatian Meteor Network cameras. It's about 5,800 meteor detections, and we used the Croatian Meteor Network cameras because their network of 15 cameras has 16 millimeter lenses, which helps them detect even fainter meteors. Our data set has 13 features in it, none of which are based on orbital parameters. So every feature in our data set is based off of the observed properties of the meteor as it enters the atmosphere. And we're using a smaller data set to develop the model, which we hope to apply to larger subsets of GMN data or even the entire data set. An overview of the methods that we tried a number of different methods, but the methods that we finally kind of converged upon is to normalize the data with the sklearn normalize function. And then we used, for dimensionality reduction, we use principal component analysis, or PCA, which reorients axes along maximum variance and reduces features while preserving key patterns. And then the clustering algorithm we settled upon was k-means. And k-means groups data into user-defined number of clusters, which is what K stands for, by assigning points to the nearest cluster and then updating the centers to the average and repeating this until the centers of the clusters is stable. Some of the methods we tried that didn't work. The methods you see on the left, TSNE and kernel PCA, are dimensionality reduction techniques. And we tried TSNE because what it's supposed to do is preserve some of the nonlinearity in the data set. Since a lot of our features had Gaussian distributions to them, we figured this would be a good option for us to use. But we found that after we normalized the data and we did the dimensionality reduction, this essentially made each feature linear anyways. Kernel PCA gave us similar results, but we found that linear PCA, it's easier to back out the mathematical model of what's going on there. dbScan and HDBScan are both clustering algorithms that work fairly similarly. And so dbScan groups points that are close together based on a user-defined distance. HDBScan does this almost automatically. But they start with a point, expand to a cluster if enough nearby points exist within that distance, and repeats this process until all the points are checked. And then any point that doesn't fall into a cluster is marked as a noise point. We found that with the two scan methods, that the algorithms don't work very well when clusters aren't clearly defined. And after we ran dimensionality reduction on our data set, we essentially had a clump of data. So that's why dbScan and HDBScan didn't really work very well for us. So with PCA, what you're trying to do is preserve as much of the variance as possible. And you want to have as many components that will preserve typically up to 95% of the variance. But we found that with 5 components, that captured almost 100% of the variance in our data set. And then for k-means, in order to find the optimal value of clusters that you should pass into the method, you use this method called the elbow method. And it helps find the optimal number of k by plotting the cluster cost, which is inertia on the y-axis for different k values. And then the elbow point, where the cost stops decreasing sharply, suggests the optimal k value. So we could have used k values for between 3 to 5. I tried k values of 3, and I didn't feel like it gave us enough kind of structure when we started looking at the clusters that k-means found versus the physical parameters of the data set. And then when we used 5 clusters, we started seeing too much blending together. So the plot you see here on the left is kind of a traditional beginning height versus initial velocity plot of the meteors in our data set. And we've colored them by the 4 clusters that k-means found. And cometary meteors usually plot up on the top of that strip you see there because they have higher beginning heights and are typically faster when they enter the atmosphere. What we found was very interesting was this cluster that we think is iron meteor or asteroidal meteors. The blue cluster, light blue points there, very similarly resembles this plot you see on the right from a Mills 2021 paper where they looked at iron candidates in their data set. So we think that cluster number one, or those light blue points you see on the plot there, are asteroidal meteors. And then when we look at the data set plotted with our calculated KB values versus Tisserand, so Tisserand is an orbital parameter, and anything greater than 3 is pretty much asteroidal, and then anything less than 3 is most likely cometary. We found that our light blue points pretty much plot where we would expect our asteroidal meteors to plot up at, with the KB value greater than 7.3 and a Tisserand larger than 3. And then our cometary meteors, we found a cluster there, which we think is cluster number 3, plotting with KB less than 7.3 and a Tisserand less than 3. So some of the next steps for this project is to develop the mathematical model of the algorithm. So we want to back out basically an equation from the PCA analysis that we can define to quantify meteors very similarly to how KB works. And then we want to use this new model to compare to showers with known parents, such as the Geminids with 3200 Phaethon, Orionids and Eta Aquariids, and the Southern Delta Aquariids. And then some of the key takeaways is that we found that this machine learning algorithm finds physically meaningful clusters. And the model is based on physically observed parameters with no prior assumptions, and also no orbital parameters fed into the algorithm. We want to back out the mathematical model for future years, and we want to apply this model to other showers with known properties for confirmatory testing. Thanks.
Amazing talk, Sam. Thank you. Yes, results out of nothing with minimal assumptions. That's what we want to see. All the other models have some, theoretical assumptions, et cetera, but this is pure data, and that's what it makes it so impressive. Are there any questions for Sam? Alex, go ahead.
Oh, hi, Sam. So great to hear about another machine learning stuff. Yeah, I do actually develop some really simple machine learning stuff because my app is really just some spoilers. My app is trying to take pictures of meteors and by just leaving your phone on the deck, pointing upwards. And I want my hang on, what's that again? My machine learning algorithm to identify meteors. Does your machine learning algorithm detect, can fit inside the phone? Is it really small?
So this is just using orbital data from the GMN. It's not doing anything off of the images or anything like that. It's using the data set the public data set that's posted on the GMN website. I filtered out some of the detections so we can just look at the smaller data set from the Croatian Meteor Network, and then fed it into some of sklearn's machine learning algorithms. And now that we're seeing that we can get some physically meaningful results based off of the numbers that are extracted from all of the meteor detections, we're going to dive a little bit deeper and see if we can develop a mathematical model based off of what the algorithm is doing.
Thank you so much. We have to move on to Marshall. If anyone has any other questions, please put them in the chat, and I'm sure that Sam is going to answer them. Marshall, go ahead.
Yeah, let's get the screen running. Ooh.
Yeah.
So, are those boxes appearing?
Yeah, there's a box in the upper left. I don't know if you can maybe do something about that. we can ignore it. It's not a deal breaker.
Yeah, gives us the.
Okay, now there's one right in the middle.
Oh,
Okay,
should be
all
gone
good.
now.
Looking good.
Yep.
You're good to go.
Cool. Okay. Well, yeah. Thanks for joining me here. I'm going to just sort of run over the story of us locating New Zealand's 10th meteorite, which is now named the Takapo meteorite. And this image here is the fireball that dropped the rock, captured by Dennis Behan, and we've got some nice footage of it coming in. So yeah, our network we sort of set up in 2022 with 6 cameras active, and then it grew from that to 122 cameras in 2024, just after we had found Takapo. And now we're currently sitting at 153 cameras listed on the GMN status page, with about 80% of those sort of working properly. And we sort of the map you see here is showing the coverage we had at around 2024 April. And so it was pretty good coverage across the whole of the country, with just a couple of gaps, maybe about here in the east coast of North Island and down in Fiordland. But yeah, we set this up with the goal to find New Zealand's 10th meteorite, now New Zealand's 11th, and as well as contribute to meteor shower observations. And we've had success in both areas, so it's been great. The sort of story of the Takapo meteorite starts with Dennis Behan sitting in his spa pool in Queenstown, and he was watching the sky and spotted this fireball. And fortunately, he has a camera mounted on a post looking in exactly that direction. So he jumped out of his spa pool, ran up into his house, and started messaging everyone on the network and looking for other cameras that may have detected it. And so this is a bit of footage from his camera of the fireball coming in. It's pretty cool. Would have been a pretty awesome thing to see. And then this is another one of our cameras. Oh, sorry. Whoops. The NZ 0015. Another good image. And we had about 4 stations at the time picked this up initially, and then we added a few more cameras from other parts of the network later on. But we had enough to get a trajectory, and I think Dennis V did Jesse State, and we had Peter McKellar had calculated a trajectory by about midnight that night. So that was a Wednesday night. The fireball was observed at 9 p.m. And yeah, by midnight we had a trajectory. And this is sort of the southern end of New Zealand here, looking towards Dunedin. Dennis Behan's camera is located here in Queenstown. And this was the sort of details of the fireball flight path. So we initially detected it at about 100 kilometers height, moving at 17 kilometers per second, and managed to track it right down to 25 kilometers, where it had decelerated to 3 kilometers per second. And the event lasted about 7 seconds that we were able to capture. And you can see at this point, we sort of had an idea that it's probably dropped a rock, and that it's fallen into a part of New Zealand that doesn't have a lot of mountains or bush or farmland. So it's looking like a pretty good candidate for a search. Following that, there were a few iterations of the dark flight modeling. On this one, I think, was the most recent one. And they sort of had this scatter of masses south of Lake Tekapo, within the Tekapo River Valley. And so this area was 13 kilometers long and 3 kilometers wide, with the biggest masses located to the western side. And we figured if we're going to do a search, we're going to focus on the larger masses. And fortunately, that area there is mostly within public land, which made the logistics of organising a public search much more simple. We did contact the farmer who was located just northwest of this dark flight model, and he was very unhappy about the idea of public members of the public walking around on his farm. So we got quite lucky there. So meteorite came in on Wednesday. And Saturday, me and Dennis Behan went out to check the site, and this is what we saw: flat, barren land, with the ground is this light grey brown silt with these dead boulders of greywacke. And for New Zealand, this is one of the best places you could hope to go looking for a meteorite. Most of it's mountains and bush, and there's some of it's farmland with various levels of grass height. So this is just a prime location for searching. That's my boot scale, and we decided we'll organise a public search on the following Thursday, 21st of March. So this is the area that we decided to fixate on, sort of marked up with this white box. This is all within public land. And this is our second public search. So we had been sort of developing how we approach these searches. And in this case, I'd actually pulled in some of the strategies that New Zealand Land Search and Rescue use to locate people, or things like bullet casings in grassy fields. And what they do is they break up search areas into a grid. In this case, we used 200 by 200 meter boxes. And we had 24 people turn up to the search. So we split them into 5 groups, parked vehicles there, and had everyone walking out to their first search boxes. They were supposed to search a box, let me know, and then I'd send them to the next box. And we decided to start here because this was the highest probability area. But as the groups were walking out, only within about 20 minutes into the search, someone spotted a strange black rock on the ground and sent me a picture, and I was a bit shocked to realize that we've probably found it already. Found it. So this is Jack Wetterings here, standing in front of the meteorite that he spotted, and a lot of smiley faces on the day, and a lot of celebrations going on. It was a pretty exciting time. And this is an image here of the rock in situ before we touched it. You can see it's got sort of a dark surface and rounded shape, very distinctive to that greywacke. And it's got a pale interior with this thin fusion crust on the outside. And fortunately, that chip was there on the surface, so I could, identify this almost straight away. I also happen to have a portable X-ray fluorescent spectrometer with me, which could give you the chemical composition of the surface that you analyze. And most meteorites will have sort of 1 weight percent nickel. This gave me 0.5 and 0.9 weight percent for 2 tests. So at that point, we were like, yeah, we've definitely found the rock. This was the first time I've ever had to identify a meteorite in the field. I've seen them in the lab before, but it's sort of a bit different when you're out in the field. So I was pretty happy with that. We've since classified the rock. It's now listed in the meteorological bulletin. And I've sort of done some of the analyses here at Otago University using our scanning electron microscope to get this L5 ordinary chondrite classification. And I've just got like a nice photo here showing the sort of micro texture of the rock. So we've got a couple of chondrules. There's a coarse-grained silicate matrix surrounding these chondrules, which are quite well defined. And then you can't really see it well, but there's these iron nickel alloys that these little bits of metals sort of scattered through the rock and some iron sulfide. So scale down there of 1 millimeter. So yeah, pretty cool. This represents the 3rd fall that has been found in New Zealand, with the previous one being the Auckland meteorite that fell through someone's roof. So that was an easy one to find. And after that, the last fall was the Makoia in 1908. So in this case, it's probably one of our best documented. It is our best documented meteorite fall in New Zealand. So cheers. All thanks to the GMN.
Thanks so much, Marshall. Are there any questions for Marshall?
Marshall, do you want to tell us what's going to happen with Takapo?
Oh yeah, well we've it's going to be put on public display at the Otago Museum, so down here in the South Island of New Zealand. Yeah, that's the place where it's going to be for the distant future, I guess. Yeah, it's pretty cool. Yeah.
Good, thank you. If anyone has any other questions, feel free to put them in the chat. Okay, and now we have Derek. He's gonna tell us something about his meteorite search, which is ongoing.
We weren't quite as successful as Marshall, but we'll go through the process. Uh, okay, so I'm going to try and share my screen here. Okay, so can people see that okay?
We can see your screen.
Slideshow.
Yep.
Yeah, that's coming up. If I can get that full screen or something. Hang on. Yeah, that's it. Is that better?
Yep.
Okay. So we had a fireball. We've seen several fireballs before, but this one was observed by Hadrian at Curtin University with the two DFN cameras. So uh, so these are the two DFN cameras. They're an all-sky camera, but they're very high quality. So this is recorded. So that's one of the DFN cameras there. Let's go to the next slide, and a similar sort of trajectory. Okay, so Hadrian observed this and very quickly realised it was quite a slow-moving um, uh, meteor and would have almost certainly dropped somewhere. So that got us pretty excited. And we're quite data rich. Was also picked up by All Sky camera just north of the event. You can see this one here. The same guy's got a GMN camera, but it wasn't operating. So, and he got a security camera. So that's the meteor on the security camera. So we're quite data, and it was also picked up by a number of all sky cameras and excuse me, uh, security cameras in Melbourne. So we got a lot of information. So we had a look at the timestamp that Hadrian had, and sure enough, we'd picked it up on 4 of our GMN cameras. The best of those was at Tokamo, where we've got a really good identification of the tail. We've got Goldie, which is just north of Melbourne. A little bit of moon in there, and Pasco, which is again Melbourne. And this one wasn't used in the analysis, but it is a lot. I was interested in the comments before about bats and moths and God, you can see all the rubbish in there, but you can see the meteor in here at the same timestamp. And it's a conniver, so that's about as far west as you can get in Victoria. We've got 2 cameras out there, and they're providing very useful. So we've got lots of data on this, and we're a little bit time constrained. Hadrian at Curtin University used the 2 DFM cameras to come up with his best indication of a search area here, which is just east of Ngambie, not far from Murchison, the famous Murchison meteorite. So he came up with this search area, and Andy Tompkins and Rachel are based at Monash University. They went out and searched this whole area on the 14th and 15th of December because they were about to go to Antarctica to look for meteorites. Didn't find anything. At the same time, Peter was doing analysis in New Zealand for us, the same sort of information that you saw from Marshall before. Again, it sort of showed it had quite a low velocity when it went into dark flight. Able to look at ground tracks and whatever. And also Dennis and his student were looking at helping us out with developing the dark flight of the meteor, quite separately from the work that Hadrian had done. Um, uh, so, so Dennis initially did an analysis based on the four GMN cameras and came up and Dennis will correct me, but this is where it goes into its dark flight and then allows for a wind drift and projecting a strewn zone in this area. And both Dennis and Hadrian, they're talking to one another and they agreed it was probably about 100 grams and likely a single meteorite. Um, so so then, so this is the area that Andy and Rachel had searched, and the strewn zone that was being suggested by Dennis, and Dennis. Now this is based. Dennis subsequently got the DFN camera data and the GMN, combined them, and there was some discussion about wind models. And anyway, his Dennis's best estimate was this area in here. And given that we're talking about 100-gram meteorite, plus or minus 50 grams, perhaps we're probably looking in this area here, which is nowhere near the search area that Rachel and Andy had a look at. So we looked at it, encouraged by Andy and by Hadrian, we said, well, look, let's do another search in this area here. So this is a blow up of what we think is the most likely area based on Dennis's advice. And we met around here somewhere, and we didn't look at the area where it's sort of a lower weight. We sort of focused on the area where along the strewn zone and around about 100 grams. So we basically searched in this area initially, and then subsequently in this area in here. And I'll show you. There's a further blow up of that. Okay, so this is Charles Creek. So that's another blow up. So we've basically searched. We started here, and we basically searched this area here, and then subsequently we moved to this area here. We basically searched everything from this drainage line here down to the road, searching that area. So I'm just going to share with you if it comes up. Yeah, okay. This is Hadrian encouraged me to do a video log of the search. So this is what I came up with. So there's just a bit of this you've already seen. So that's the meteor in the security camera. There's the DFN camera images. So that's the Tocomole, Conniva, the GMN images that you saw before, just zoomed in a bit, Pasco, and Tamlu. So you've seen all this. So that's the meteor map. So we're looking at this meteor here. That's some of the trajectory work that Peter did. That's the height. That's the track that Peter determined, and the orbit. And probably this is the important data, that analysis that Hamish did before. So I'll just pause this here maybe. So this is the strewn zone. I intentionally haven't blown this up because it's public information. I don't want people searching out it. So we sent a note out to the 3 landholders. Not such a nice area compared to the one that Marshall had. You can see this is awful country to be finding meteors in. We did find a couple of snakes, so there are OH&S issues. This was the second area, which was much better, If it was a meteor, they would have definitely found it. We recorded our track of the meteor and did a sort of a police search type thing. I've done searches with Andy before, so I sort of knew more or less what to do. They were off in Antarctica, and no, didn't find a thing, but we tried. So, and there's some acknowledgements at the end. So that's not as successful as the search for Marshall. It's not quite the end of the story here, because um, it's I still think it's quite likely there's a meteor out there somewhere. I'm waiting. Andy and Rachel are just back from Antarctica this weekend, so I want to get. I want to. Um, I want to sit down with them and just go through a debrief. And I I still think it would be nice. Sorry about the phone in the background. I still think it would be nice to just have a look at this data again and just see whether we can collectively come up with a better identification of what the search area is. You know, when you're committing time and resources into searching, you want to be pretty confident, where the Stirring zone is. So, and we're not, uh, I mean, it's interesting from a scientific perspective that we've had sort of independent analysis using two different modeling approaches, and that's interesting in itself. The real ground truth here is if we had found something, it would have really allowed us to support one of the alternative modelling approaches. Dennis might want to comment on the wind. I have a lot of awe in the work that Hadrian and Dennis do in this stuff. It's very difficult to determine Stirring zones for this sort of event, given the lack of knowledge you have about the object. But anyway, we've tried. So it's not quite the end of the story. Andy and Rachel might come back and say we want to do another search in the areas we haven't looked at, and we might do another analysis to see if we can refine that Stirring zone a bit. But that's probably enough from me, I think.
Amazing. Thank you, Derek. Yeah, so it's good to have one story of a successful recovery and another story that just raises more questions than gives answers. That's for sure, right? Yeah, so what you've seen in the diverging predictions of the strewn field, it's uh, I wouldn't say it's I mean it is a bit unusual, but the strange thing is that Hadrian and I were using the same input parameters and the same wind model. So I guess the only difference is it's some basic assumptions and how the wind interacts and the shape of the rock, although we weren't really able to reproduce each other's results. I do have a version of the Darklight code that I'm working on. And the idea is that at some point it would be released out in the wild, but it still needs some how can I put it? Testing and validation, because I don't want to lead people the wrong way. So, okay, Steve, you have a question?
I
Go
think,
ahead.
yeah, well,
Derek,
maybe a comment. I'm a bit
oh,
of,
sorry.
if I just make, I'm a bit of a babe in the woods compared to the work that Dennis and Hadrian do. But I think there are two sort of unknowns. There's the final point of the meteor where it goes into dark flight, and then there's the wind drift is the unknown. So I think the GMN data, because it's a finer meteor, finer identification of the tail, it probably gets us that point at which it goes into dark flight more accurately. So anyway, there's more to talk about on this event, but I appreciate all the work that Dennis and Hadrian do. So yeah.
Thank you. Yeah, I believe that I sent Hadrian the same endpoint. So it's not that it was computed from two different trajectories, but yeah. Sorry, Steve. You had a question. Go ahead, Steve.
Yeah, just before the question, Derek, on that point, I think with Takapa, I think Jesse State would know better than this, but we had a relatively low wind night. It was fairly still, and we had good wind data from a station in Invercargill. My question was, what was the sort of area in hectares of those two search areas that you searched?
Sorry, that last bit, Steve, can you just repeat that?
Yeah, just what sort of area in hectares or acres were you searching?
Oh, okay. So those two search areas that we had a look at, the first probably would have been about 10 hectares and probably about the same for the other. So, relatively large areas, and we're still not covering all of the stream zone.
Okay.
And the other area that Andy and Rachel had looked at, I don't know the size, but I would expect it would be. They spent all weekend looking, just the two of them. My guess that would have been probably about 20 hectares.
Thank you. Are there any other questions for Derek? Okay, well, if not, we are going to have a short break. We've been talking for well over an hour now, and we are going to reconvene in 20 minutes past the hour. So thank you, and see everyone in a bit. Okay, Gene, I think you can share your screen and we can get ready.
We
Okay,
good to go?
yeah, I think I can see it well, and maybe we can just give everyone a few more seconds to just to come back from the break, and in case they're not back. And okay, I think you're good to go now.
All right. Well, good evening, everyone, in the other hemisphere, and also in the evening time here in the Western United States. I'm going to talk today about a what is really our first initial foray into an exploration of whether RMS can shed any light on what the local light pollution environment might be like around within the field of view of our GMN cameras. And I got this idea because I've known because for a while now Dennis has been as part of his flux measurements capability uh, produces something called what he calls a stellar limiting magnitude as determined from the field of view of the camera. And there's also, of course, many of you are familiar with probably the unihedron sky quality meters, which produce something that they call naked eye limiting magnitude. So it turns out that the New Mexico Meteor Array here in New Mexico has one location where both those instruments reside at the General Nathan Twining Observatory, which is the club observatory for the Albuquerque Astronomical Society. And that observatory is located a little bit south of Albuquerque at this location here on the map. And you can see here the field of view of our of US00G, our GMN camera there. And the red circle approximates the field of view of our SQM sky quality meter at that same location. So there's not complete overlap, but there is some partial overlap of the field of view of those two devices. Now, the two sensors, of course, are quite different. I just noted the difference in the field of view of the two sensors. Um, the Probably the one big difference is that the IMX 291 camera does not have an IR filter, whereas the sky quality meter has an IR filter in place. So I think they have very different spectral sensitivities. And the other difference is in their data acquisition rates. While the RMS cameras are set up to collect stellar limiting magnitude data on 5-minute averages, but the way we had the sky quality meter set up at the site when we started this experiment was at 20-minute intervals. So we did 3 different periods of comparison on 11 moonless, Milky Way-less, and generally clear nights around the new moons of November 29th to 1 December, 29 December through 31 December, and 27 January through 30 January. So the first moonless period, new moon period, was in November, and this is a plot of magnitude. The blue dots on top are as determined by the sky quality meter at 20-minute intervals, and the red circles down here are stellar limiting magnitude as determined by RMS on the 20-minute at the time on the clock that was closest to the measurement time by the sky quality meter. And you can see, first of all, you can see that there's about a 0.6 or half a magnitude differential, whereas the sky quality meter is giving us magnitudes of about around 6.2, whereas the RMS is giving us magnitudes of around 5.6. But you can see that there is at least somewhat of a coarse agreement between the patterns of the nightly pattern of the 4 nights through the 4 nights. The sky quality meter, went back, jumped forward here. The sky quality meter goes through this kind of a S-shaped curve here. We don't quite see that here on the RMS signal, but they both have minima and maxima somewhat in the same locations. We move on to the December timeframe. The results are similar. So we were encouraged by that result. we decided at this point that we needed to get off these 20-minute intervals for the SQM meter. So Pete Ishman changed the data acquisition time on the sky quality meter to 5-minute averages. The software allows that. So now it matches up more closely or exactly with the um, uh, RMS system. And so these are now 5-minute average measurements throughout the 4 nights of the new moon in January. And you see there the same difference in the magnitudes of the values of the magnitude, but now the temporal patterns start to look somewhat different. So I looked at this is now for the first period, the November moonless nights, November new moon, and I plotted the Pearson correlation coefficient between the sky quality meter magnitudes on the y-axis and the RMS magnitudes on the x-axis. We had 122 measurements. These are the 20-minute interval measurements. R value of 0.48, the very low p value. So there looks like there's some moderate, modest kind of correlation between these two measurement methods. I added in the second plot here another correlation coefficient plot, but now I've added the December data to the November data. So now we have 2 months of data combined into one plot. And so the number of measurements now jumps up to 223. The correlation coefficient improves to 0.6, so that's looking more interesting. So we were excited to then see what would happen when we add in the data from January, which was now at 5-minute intervals. So we've got much more data added into the plot, but we were kind of went backwards a little bit. The January measurements seem to be different than the November and December measurements. So now we have a correlation coefficient of 700 samples, correlation coefficient of 0.38, and it's hard to be terribly, I mean, you still have to say that there's some kind of a modest, possibly modest or moderate correlation there, but it's not terribly strong. So it raised several questions in my mind about what might be going on here. Uh, First of all, I guess I want to point out that we all see on our cameras every night this thing called the photometric offset variation. And it turns out this is directly, Dennis, and correct me if I misstate anything here, this is directly related to stellar limiting magnitude. The relationship is just a simple linear function. So, and I believe in the way we see these plots now, each data point represents one meteor. Is that correct? That's a recalibration that is done at each meteor observation. Is that correct, Dennis?
That's right. Yes. So this is done exactly as you say. So every time there's a meteor, a recalibration is done. We also have another one that's done for the flux, where it's done in a regular intervals every 5 minutes. That's the
Yeah,
difference.
and I didn't show. I'm not showing that plot.
Yeah.
But I guess I want to make a recommendation here that I think this plot would be more useful to people if it would be replaced by a stellar limiting magnitude plot. Would that present a technical challenge for you?
Wouldn't be a technical challenge, but my argument would there be that this is a direct measure and the still limiting magnitude plot, well, the function that we use is I derived it very roughly and I don't have full confidence in it. Let's put it that way. And the way what the still limiting magnitude represents is some assumptions that have been baked in for visual meteor observers. We were trying to estimate meteor flux, and the way limiting magnitude is determined visually is by following something in a visual observer's handbook, which is what I've done on our data. So that is only applicable to that application, but not. I feel that the SQM and my method have some fundamental differences, but we can discuss that after the talk.
So is it also true that the limiting stellar magnitude for each 5-second interval is that predicated on just the dimmest star in the entire field of view?
No. So the way it's computed is using this photometric offset, right? And the photometric offset is tells you where that 0 point is, where the cutoff is going to happen, right? So it doesn't assume what, or it doesn't have to measure or see the faintest magnitude in the field of view. It's using a bunch of stars to estimate where that 0 point is because it's going to intersect the intensity of zero somewhere. And it's really a question of where do you cut, where do you make that cut? Are you going to make a cut by some signal to noise ratio or some other way? But again, we can chat more.
That leads me to ask the question, would the average peak field sums be a better measure of light pollution averaged over the whole field of view than stellar limiting magnitude?
Well, we can make a few different arguments here, but what I would say here is that this is a full frame photometry. So this is a sum of everything, of every pixel intensity in the whole field of view without any background subtraction. However, the photometric offset is using background subtracted star intensities. So my argument is that the photometric offset is a better measure because it's only measuring the total light of a star versus everything in the field of view, including the background. And that way you also get rid of,
The background is the light pollution, right?
well, yes, that's true, but the total sensitivity that you're getting gives you the limiting magnitude, right? So, so
So,
one thing, yeah, mhm.
well, it seems to me if the field of view, the field sums integrates over all the light received into the camera,
Yep.
whether it comes from stars, meteors, or light pollution.
Mhm.
But in a cloud-free environment, the minimum value of the field sum ought to represent the darkest total, the darkest moment of the sky that in that measurement period.
Yes, so that's technically true. However, plus the the dark noise of the camera that is not being accounted for. So if you can fix the gain or guarantee that the gain doesn't change meaningfully, which I think we can assume for the darkest part of the night, and we are able to measure what the quote unquote dark frame is, the value of the dark frame, and you subtract that, then yes, that would
Okay.
be a good measure then.
We could figure out a way if we could put a cap on the camera every night
Yep.
somehow automatically and get a dark frame, then we could do something like that.
Yeah, you can have like an automated iris, and then you close it, you take the measurement, and you open it. That's it.
So just to wrap up then, we saw a moderate correlation between the RMS stellar limiting magnitude and what the sky quality meters refer to as naked eye limiting magnitude. Despite the significant differences between the two sensors, we think a better experiment would be to aim both instruments along the same altitude and azimuth so that they're measuring more exactly the same piece of sky. And as we were just discussing with Dennis, I want to explore the utility of using the field sums as an alternative way of looking at light pollution. So thank you for your attention, and happy to entertain any questions or discussion. Thank you.
Awesome. Thank you so much, Shane. We are running a bit late, so if anyone has any questions, please put them in the chat or wait until our break, and then we can have a big discussion about everything. Okay, next up we have Alex. So Alex, can you please share your screen?
Oh, you can hear me, right?
I can hear you, I can see you, and we just need to see your screen now.
Okay, sweet. Hang on just a second. I will just before I share my screen, I would like to talk to you about a bit more about some stuff
Go
before
ahead.
I share my screen. Yep. So First of all, thank you so much for giving me an opportunity to speak. I am Alex. I'm 16 years old, and I'm based on New Zealand, Auckland. And yes, I'm a passionate app developer and also an astronomer. First of all, I would like to say where it all came from, where the also idea of my app came from. Came from going to the Royal Astronomical Society of New Zealand's conference, and I done a talk. I'll just share my screen right now. Oh, hold on. Share. Apply system settings. Sorry, I didn't. Zoom later. Sorry, I might have to postpone it for 2 minutes. The permissions, it's just something going on with my computer. I'm so sorry about this. Mind if I just give me 2 minutes? Yeah, sorry about that.
That's perfectly fine. I think that maybe we can have a short discussion about SQM and measuring the limiting magnitude and and the associated things. So we can. Um, oh, okay, you got it.
That's awesome. That's awesome. Oh, sorry.
Okay, no worries.
Here, this is my app's icon. I want to discuss what my app is all about. My app, like I said, my abstract is about making this a simple machine like this, an iPhone over here, a meteor camera. It is just very simple. But how can this be a meteor camera? So I did a talk at the Rassens conference. This is me, and at the conference, I spoke about an app I made previously, which is called Little Planets. And Little Planets is the first app I developed. It is dragging planets into a solar system in order, and it is available on App Store. You can check it out. I won't discuss too much about it because it is a bit of task. And this app, after I did a talk, two gentlemen was so nice from Fireballs Aotearoa. One of them is actually in this meeting right now. He's Marshall. Thank you so much. And the other person was Dennis Behan. He's the person who spotted the meteorites shooting, grazing the sky. No, not grazing, sorry. Yeah. And they came to me and said, "Hey, Alex, can you create an app for us?" And I said, "Yes." And that's how I knew Fireballs Aotearoa and Dennis himself, which is my honor. And first of all, for my app, in terms of my app, here, can you see my app? Can you see a phone?
Yes, we can.
Awesome. And this is my first tab I would like to show you. You can see there are a lot of meteor showers on it. If you scroll it, it feels like looking out of a spaceship, like the windows. You see all of those meteor showers? Yeah, and this is all over the year, such as Quadratus. There are some very important meteor showers included, such as Quadratus, Geminids, Andromedas. Well, maybe not the most famous one. If I click into one, you can see this. This is the top is the name, how much meteors they have per hour. Oops, 0 because it is not active. And constellations, the constellation, the meters per hour, the origin. I can go to a better one. For example, Eta Aquarius is from Aquarius. You can see it's from Aquarius. The origin is from Halley's Comet, light pollution. Well, this is not based on locations because it does not work on emulators. Here, you can see moon phase, sun position. And the fun part is if you click into constellation, it displays things about constellations, how much meters per hour, and the graph. It can't show it right now because it does not work on laptops. I'm sorry. And origin, the Halley's Comet, all of these, all the information about Comet, and some viewing tips. Just to show it works on people's phone. Can you see my phone? Here in Alpha Centaurus, you can actually see how much meters it has per hour. In this case, 1. It's not very active in this time of a year. Secondly, I want to show you is the locate tab. You can see this is a road map. Here, let's go to Australia. You can see all those yellow things. These are meteor trajectories. And this, in the laptop, sadly, it cannot zoom in. And here, you can see it on my phone. You can zoom in, and all these streaks represent a meteor. And these are data coming from the GMN, which is this organization, which is awesome. And here comes the most important part, most important tabs out of all of them. It is a camera tab, which I will come back to my slide. I'll see that one. So sometimes you see meteors and you have your phone, but as soon as you see it and yell out meteor, and it's all gone. So I want to make this a bit more accessible because when you pull out your phone, take a picture, it is all gone. But my app can help you do that by taking, this is like the camera tab, just a press of a button and let the machine do the work. But how do you do that? You put your phone lying head up, facing up on the deck, and press a button and come back later around 10 minutes, maybe 20, a few hours, maybe even overnight, and watch the magic happen. See a lot of meteor pictures on your phone. But how do I do that? First of all, here's my slide. It takes a 10-minute video. Secondly, it runs my code and stacks them. Here you can see the stack picture. This is a meteor. 10-second video, take a video, stack it. Then the stack image is over here and sent to machine learning for classifying, is it good? Has a meteor on it, or it doesn't? Next up, what is machine learning? Yes, I believe Sam did a very nice talk before, and it's about machine learning too. I would like to show my own machine learning model. Hang on, which is over here, just right here. This, I call it Meteor ID, and it accepts input of like images. Here, you can take a look. This is an image I got from internet, and here you can see a meteor. You can still see my screen, right? Yeah.
You can.
Here, and you send it, processing. Ta-da! You got a meteor. It identify the meteor and the exact position where it is, and that is very difficult for me to train because machine learning, they are based on data. It's just like how our brain works, how we look at images and classify it. I have to curate the data very carefully and give it to the machine, and it has to train. And it's a very long process. Here, another picture. See, you got a meteor too. So the machine learning can can classify the pictures to tell the phone which one to save and which one isn't. Because without the machine learning, the next thing you want to you realize when you pick up your phone after overnight, it is going to be full of useless pictures, and we don't want that. So that's why my ML exists over here. And my ML is put as so small, around 30 megabytes that can fit in a phone and classify it in seconds. So it can maximize its efficiency in meteor classification. And my future aspirations for this app is I'm going to apply for Apple's Swift Student Challenge. It is a coding competition organized by Apple. I'm a previous winner actually, and I won the competition because of the previous app I made called Little Planets. And currently I applied for an Ames Award. It is a funding award organized by the North Harbor Club. I won't go too much into that. And I hope my app can be sent to the general public, scientists, for them to do cutting edge research by just providing them some data. Just click of a button, face up your iPhone, and then take a picture and then take a nice video. and overnight, watch the magic happen. Another thing is a bit more, this is the app icon I drew. You can see the crux over here and the pointers, the 2 stars, and a hopeful little child looking up the sky. And this really highlights about how such a little child can contribute to something so much bigger. And I'm not very sure if you can imagine, but you can imagine there is a meteor striking across the sky because the kid is still waiting, anticipating for a meteor to strike across the horizon. And to conclude, I would like to talk about the name of my app, Make a Wish. It is something that I truly loved. Where they come from is when I have hope, I go to my deck and look for shooting stars. As one pierces the sky, I make a wish, hoping the shooting stars will wash away my pressure and bring me hope. The app's name stems from a childhood wish. I want to make a positive impact. This wish blossomed into a mission to inspire and enable others, whether a scientist seeking groundbreaking discoveries or enthusiasts dream of their first meteor sighting. A Make-A-Wish is about creating moments of delight and wonder. A quote by Steve Jobs, Apple's co-founder and former CEO, continues to inspire me. It's in Apple's DNA that technology alone is not enough. That technology was married with liberal arts, married with humanities, that yields out the result that makes a hard thing. And that reminded me to make an app that is not only an app, it is something that brings hope and something that brings the light to everyone, not just scientists, but everyone, the community. So this app embodies that aesthetic, marrying technology with inspiration to turn fleeting wishes into extraordinary experiences. Thank you for giving me such a great opportunity to show you my work. If there's anything I didn't mention very clearly over my talk, feel free to answer now. Thanks so much.
Well, thank you, Alex, and thank you for the pep talk. Are there any questions for Alex? Okay, well, yeah. So, Gene, go ahead.
Well, Alex, I have a comment and a question. And the question is, when you run your camera pointed up at the sky overnight, how long does your battery last?
How long does, sorry?
The battery. How long does your battery last?
Battery. Usually an iPhone. Thank you so much. That is a very good point. I haven't really thought about it. Yes, usually iPhone's battery can last for around few hours, probably around 3 hours minimum.
3 hours, so it wouldn't get all night then.
Yes. However, my app does work if you charge your phone, place it on the window, just as here, you place on the window and charge it here overnight, and it can still work because the ML is object detection. So no matter where the meteor is, what the background is, it can still detect the meteor and save it. So
well, my comment is I think this is a very creative idea, and I'm thinking about it in the context of I judge science fairs in a local school system, and I think it would be great if every kid who has an iPhone in a classroom would put your app on his phone and aim it out his window one night and record all the meteors that they see, and then bring it into school and share that excitement with their fellow students and create a really nice science fair project. That would be really nice to see. So I congratulate you on your creativity and your enthusiasm, and I wish you the best of luck in your endeavors.
Thank you so much, Gene. Thanks a lot. Thanks for the kind comments.
Awesome. Well, thank you, Alex. If anyone else has a question for Alex, feel free to put it in the chat. And now, according to the schedule, we have Pete Eschman. So, Pete, go ahead.
I might interrupt. Yeah, I forgot to say, if you would like to contact me anyway, I just put my email in the comments. And yeah, stay tuned because that's the most important part I forgot to mention. Yeah, I put my email inside, and once it's actually released, which will be in later this month, you'll be the first to download it.
Amazing work, Alex. Thank you so much. Pete, you're good to go.
Okay. Can you hear me and see this all right?
Absolutely.
Okay. Hello, my name is Pete Eschman, and I'd like to discuss our local meteor camera array and also the roles and potential duties of an area coordinator. We started our GMN adventure in 2018, and I've served as area coordinator since then. I've had a lot of help from other camera owners, including Steve Kaufman, who hosts our monthly meetings, Gene Mraz, who helps us optimize camera field of view coverage, that Gene spoke earlier, and then Steve Welsh and Bob Huffnagel, who have helped build cameras. We have 16 owner-operators in 11 cities. Just for reference, the surface area of New Mexico is about 15% more than that of New Zealand, but our coverage is much more sparse since our puny number of 29 cameras is only about 16% of the 153 cameras in New Zealand. So you guys have us beat on that. Our 29 cameras have 16 running on 7 Ubuntu 20.04 PCs. 10 are on Pi 4, 2 of which have upgraded Buster to Bullseye. 1 is still on Pi Jesse, and 2 cameras we need to relocate. We plan to add 2 more 6-camera Ubuntu PC systems, extending our coverage to the southeast, which would be this area. And also, we have 1 camera in Creede, Colorado, and they plan to add some more cameras in that area. Soon after we started, I learned how difficult and time-consuming it can be to monitor a bunch of cameras by logging into them every morning. Then, for a time, we moved to automated daily upload of station data to a local server. I use scripts run as cron jobs to gather and upload our server data summaries so they can be viewed in a local website. Now, I use a cron job on my multicam Linux system to download the HTML files for the US from the GMN weblog. It calls a small Python program to create subsets that only include our cameras. This is done by looking for NMMA at the beginning of our camera weblog descriptions. The Python program also creates a version sorted by camera azimuth. We can easily sort by camera azimuth because this is also included at the end of the weblog description for each camera. Next, both HTML files are uploaded to a local website where results can be viewed by camera ID or by camera azimuth. We found it's easier to spot shared meteors when you view images that are sorted by camera azimuth. We include the number of meteors in the title of the detected stack. I also create a version displaying FF interval plots in place of the captured stack. This provides a quick way to scan for systems having recorded problems. I also have created HTML summaries that reference data from the weblog static pages, which is really quite handy since those links do not change from day to day. Our local website is refreshed 3 times a day and is a resource for public outreach as well as error checking. Each morning, I rename the previous day's HTML files to the corresponding day. This way, I can review results for any given day simply by picking from the index all of the HTML that was generated for that day. The whole process does not take a lot of resources, and a Pi 4 can do it easily. Steve Matheson's excellent camera summary page is available now, and I check our cameras on it every morning. And Steve, you're probably better equipped to describe this, but now that this resource is available, I use our local website summary much less often. I want to thank you, Steve, for this very valuable contribution to GMN. Over time, these new GMN resources have reduced the need to upload data to our local server or to log in to our local camera systems. Nowadays, I can simply access data through GMN website links, which greatly simplifies and improves our local camera monitoring. On the status page that Steve provides, I sometimes click on the tilde symbol that is next to the camera ID. You can see them on every one of them. This magic little tilde symbol. In this case, we're looking at our one remaining Pi 3 Jessie. It's showing recording problems that may be due to an Ethernet cable connection issue, an aging micro SD card, or perhaps the old Pi 3 Jessie just can't keep up anymore. We hope to upgrade this hardware soon. But this is a tremendous resource because for any camera, you can review all this stuff in one shot. It's wonderful. We use a local script, which is called automatically at the end of RMS processing. The script writes summary diagnostics to a small text file, adding one line per day. Diagnostics include the number of captured FITS files at any shortfall from expected total, the number of meteors in the detected stack, a warning if the photometry plot is missing, or if there's only room for one captured files directory. It's important to have a good number of captured file directories so that you can locate data from a recent firewall. Sometimes we make text entries in this file to note hardware changes, since the file serves as a great history log. Next, the script uploads the diagnostic summary to two local sites. Then it cleans up old data and data directories, and finally backs up the NITAR BZ2 and diagnostics data to a USB drive located on the Pi or Ubuntu PC. We've developed some utility scripts for tasks including data backup, data cleanup, local file upload, setting cameras to day mode to help focus lenses, calculating the number of files we should expect to see recorded on one given night. So that's like the projected total that the RMS total capture interval for one entire night should record. An area coordinator duties include things like use of config file parameters. Those would be the weblog description, network name, and camera group name to organize the cameras in your area. You want to automate tasks like data cleanup and backup whenever possible to help reduce your workload. You want to keep RMS updated on all stations. Use remote station connections to distribute utility scripts and local updates. Watch for any data recording issues and bright events every day. Make regular disaster backups of key files using RMS backup. You also want to help with upgrades, hardware and software problems, and fix any failing cameras. You want to relay information from the GMN forum to the local group. I find that a lot of our local owner-operators don't watch the GMN forum. So it's my job to kind of keep them up to date on new stuff going on and things to watch for. You want to coordinate with other GMN groups in nearby geographic areas. You want to distribute tasks among station owners to try to help spread knowledge and skills. For instance, things like making plate pars or correcting camera problems. You want to promote public outreach. You want to, most importantly, plan for and organize a ground search team for that day when you have a dropper hit the ground. For us, the payoff for our coordinated efforts have been 3 events that resulted in stream fields, and one recent one that almost created a stream field. One event probably dropped small fragments in the Albuquerque metro area. Another was located to the west, and the third was located south of Albuquerque. So far, we've been unable to recover anything that hit the ground, but we're trying to get ready for the next one. Thank you for your time. I'll be happy to try to answer any questions. Oh, and as luck would have it, complex.org, in the middle of the slide there, went offline a day ago. And we're having some difficulty bringing it back up because the simple power cycle on the BSD server didn't do the trick. We'll get it fixed soon. In fact, I'll probably drive down there tomorrow to try to help out. The next slide shows some tips for those who are just starting out with RMS and GMN. a lot of the stuff's pretty obvious, but really, you really need to pay attention to the weblog. You need to pay attention to the forum as a tremendous asset. Remember that on the forum pages, if you log in through a web interface, you can do searches, topic searches. You can search on keywords. You can search on people's names. You can find a tremendous amount of information there, most of which we hope is in the wiki. Some of it's in Mark McIntyre's wonderful resource for the UK Media Network. And remember, you want to participate in discussions and problem solving. We are self-supporting for the most part. Thank you.
Thank you, Pete, for the quick summary. And if anyone wonders how the GMN started, it pretty much started in New Mexico with Pete, and said Mike Mazer and I put a little camera on eBay asking people if someone wants to buy it for a few $100, and we were just asking for feedback. And you got the one, and the next thing we know, you ordered 14, 18.
Something like that.
Something like that. So that's
I was so lucky that a local person on our Astronomy Club forum mentioned your article on cloudy nights. That's how I discovered it. That was all serendipitous.
wow.
Wonderful.
That's how life happens, right? Good. Thank you. Are there any questions for Pete? Okay, well, always you can feel free to put any questions in the chat. Well, thank you, Pete. And now we have a pre-recorded talk by Dave Rawlinson, who is actually here in the audience, but he has a very cool demonstration, which is safer to do via video. So I'm going to share my screen here. Share sound. And, oh, whoops, not like this. Okay.
Which is the ability to jump automatically to.
Hope you guys can hear it.
I'd like to introduce one of the new features in SkyFit 2, which is the ability to jump automatically to a new start whilst you're doing plate path fitting. So CD source RMS source tilde V.
Looks like there's an audio problem for me here.
Oh, is it it's very quiet maybe? I can also hear it very quietly. I'm wondering if there's a way to increase the volume. I think the volume's already maxed out. I am sharing the stereo sound. I think you might just have to crank up the audio.
Shall I just try and talk through it live?
Okay, how about
the
that?
audience?
Okay,
can you hear me talking now?
Yes, I can. So how about
okay.
the video and I turn off the sound in the video? How about that?
Okay, let's try and do this. I have to remember now what I did, which,
okay.
given I could barely work out what I was doing at the time, could be interesting.
Okay.
So the purpose of this is to try and make producing plate paths using SkyFit a bit simpler, because you can end up spending an awful lot of time scrolling in and out trying to pick stars. So the first thing that I did was logged into the workstation that I use for preparing plate paths, activated the correct virtual environment. I forgot that the first time round, and then tried to make sure I was on a fairly up-to-date version of RMS. And in a moment, you'll see, yep, I'm on the master branch, which is good. So I'm not checking some development thing. And it was up to date as of January the 30th. I think I recorded this on the 2nd of February. So it was all looking good. The next thing that I do is I start SkyFit using the Python command, and I pull in a plate part from the local server that I'm working on. Now, one of the new functions that's been added is -m, mask path, and that'll become important in a moment. Because when we're creating a plate path automatically and jumping to different stars, we want to try and avoid jumping to stars which are hidden behind trees, because that gets kind of tedious. Ah, that's a nuisance. The command's off the bottom of the screen, Dennis. Maybe it's just my local Zoom. Okay. So opening the plate par, which is a bit wrong, you can see. So I'll gradually try and inch it into the right place using the keyboard shortcuts, W, A, D, and S, and then plus and minus to zoom in and out.
I think you're adding the mask here. I hope everyone can see the command at the bottom of the screen. I think the whole screen should be shared.
Yep.
Yeah. So you're adding the mask here in the video. Yeah.
Right. Okay. And now when the
Yes.
video opens again, you'll see that there's no stars hidden behind the trees.
Ah, there we go.
You see? So now that bit's blocked out. So we're not that the whole catalog has been masked where the mask isn't blank.
Cool.
So now I'll try and inch it into the right place. And then once I've got that inched into the right place, we'll try and start doing the more accurate fitting. So I'll pick the first few stars manually, just so we're getting it fairly close.
Little word of advice: the inner aperture should always be as big as the star.
Yes. Yeah, that's right. I wasn't thinking about that. This was demonstrating the next thing. And this is where I've now got enough to do a fit. So the stars run up to the right place, and then go to settings, and then click on the new function, auto pan to next star. And this is where the magic happens. And it was so hard writing this bit of code. So now I click on it, press enter, automatically jump to the next star, which means that you can get a nice even spread of stars across the field of view and do it a lot more quickly than when you have to zoom out and zoom in. So after I've got a few of these, I'll zoom out and we'll see that there's a nice spread across the field. This is where I decide that maybe I don't like this star, and then use Control and Space, and that marks a star as bad. And once I've done that, it won't try and jump to that star again. It'll try to jump to stars that are nearby, but it won't actually use that star. And those are the stars that are marked with the red squares. I'm just pointing to it now. And that means ignore that star, try and jump to the ones nearby, but that one for some reason can't be matched. You might do that if, let's say, it was a double star, or the magnitude of the star just felt completely different to what it should be. Perhaps it was a satellite that happened to be in an inconvenient location. And then you can carry on fitting, do another fit. And after the computer's done its calculations, everything should jump into about the right place. And from memory, I think that was everything. You can see it's even recorded there was an unsuitable star. And that's a fit. And I think that's about the end of my video. Apologies, I couldn't remember exactly what I'd done as I was talking through it live. But that's basically the new feature. I think that was the end of the video. So thanks for letting me present, and enjoy the rest of the conference. Good morning and good afternoon to everyone.
Thank you so much, Dave. Yeah, that's a very, very useful feature that I've used extensively. Of course, what you need to do is your plate needs to be close enough. But if you have something that needs to be improved, this is the way to do it. I've also been looking into doing things fully automatically, and I have an astrometry.net approach that actually might get us there, but it's not fully developed. I found that you can install the astrometry.net package on Linux locally, so you don't have to do it online anymore. And then it solves a field in less than a second. It is extremely fast, and you get the right orientation, you get the right pointing, and the only thing that would need to get implemented is distortion awareness. So the astrometry.net package does a rough distortion fit, which is not very accurate, but I think it would get us to this point, and then you can go in and make manual improvements and really finesse the plate. Okay, amazing. Thank you, Dave.
Thank you.
And we do have one final pre-recorded talk by Connor. So I did play this already in the first session. So I might just summarize what Connor has done. And so some of you might know that, we made the plates that the current star catalog that the GMN uses, which is based on the Gaia DR2 catalog, does not have any bright stars in it. And that's simply because the Gaia instrument saturates and they just simply omitted those stars. Now, that is very inconvenient for us when we're making plates. And then some people switch to the Bright Star catalog, which does have that, but it's missing some other things. And the truth is that it's really hard to find a Bright Star catalog that has everything that we need. And by everything, I mean proper names, spectral types of stars, proper motion of stars, magnitudes in different spectral bands, accurate astrometry, and also the probability that it is a double star. And I'm happy to report that our new star catalog has all of those things. And it's already available in RMS. You can, if you just update your code, you can use it. The only thing that you'll have to do is you'll have to change the details in the config file and specify that you're using the GMN star catalog instead of the old Gaia catalog. And I believe I did send the instructions to our mailing list about how to do that. If I didn't, please remind me, and I will send the instructions. There's still a bit more work to be done on the catalog. It does have some duplicates and it's missing a few bright stars, but we're polishing it and we're getting to a state where I think we can even write it up as a little publication, and then no one will ever have to go through what we had to go through. And the important thing to say is that this work was initially done by Dave Rollinson. He created the first version of the catalog. And then Connor stepped in and cleaned up a few things and put it in the right format. And now we're here. So amazing work, Dave, and congrats, Connor, who can't be here today. I think he's in California at the moment. But that is the summary of that work. Are there any questions about anything that we heard recently, either about the catalog or the automated picking, or really any other talks in this last session? Okay, well, if not, then I think this is the right time to take a group photo while we're still here. And I think I think I can speak for everyone that we can skip this break and we can just launch directly into our group photo and our Q&A/unstructured workshop. So what's going to happen is that I'm going to take a little screenshot of all of us here. So please turn on your cameras if you are presentable. And I will upload that to our mailing list. Okay. I think we have Luke twice, so we're already here. Awesome. Okay. I think, oh, Luke disappeared. There you are. Amazing. Okay, so I'm going to be taking screenshot in 3 seconds. So cheers. Okay, well, that's one. And then I'm going to take another one just in case. So I'm saving this and I'm taking another one. Cheers. Okay, there we go. Amazing. Well, thank you so much. They're saved. Okay. So let's launch right into our last part of the second session, and that is the unstructured workshop/Q&A. So we can discuss pretty much everything, and or any sort of questions that you have regarding the talks or GMN in general, please raise your hand and we can discuss everything. Um, I would like to start a discussion maybe with the limiting magnitude estimates. And I think that's a very interesting topic. And the question is how. Oh, oh, thanks, Mark. Sounds good. Thank you for coming, and have a good night. It is quite late in the UK. Um, that's a very interesting topic, and uh, if you read the literature, very often there isn't really a hard definition of a limiting magnitude, and it's really sometimes hard to pin down what is a limiting magnitude at what, for example, signal to noise ratio. Now, some people like to set that limit at signal to noise ratio of 3, somewhere I found 5. Some people, depending on whether they're focusing on very good measurements, they set the signal to noise ratio to 10. For meteor observers, however, the limit of magnitude was usually defined in the IMO Visual Observer's Handbook, where you would look at a certain constellation, they would give you a triangle to look at, and then you count the number of stars that you see inside a triangle, including the three corners. And you have the number of stars that you see. You look up at a table, and they say, okay, the limit of magnitude is this, this, and this. Now, if if you understand how the human eye works, you know that, by kind of looking around, you can see more stars than you can see directly. So, what is that signal to noise ratio? Is that a signal to noise ratio of, 5, 3? Is that 1? Is that even less than 1? That is a very hard thing to answer because our eye works in a different way than some sort of a linear objective camera and a sensor. So our task was initially to translate or to kind of match the visual meteor rates using meteor cameras. So what I've done is apply the exact same method. So I would, load up an image. I would see what the photometric offset is, which gives us a good idea of how sensitive the camera is to the pixel intensities represented by the stars. I would count up the number of stars that I see in the triangle. I would write that down, and I got a very tight linear relation that was relevant all the way from all sky cameras and then all the way to cameras with very long lenses that would see stars down to magnitude 10 or even 11. And that is what's baked into RMS at the moment. So, how does that translate into the numbers that the SQM instrument is producing? I'm not sure. There's also a factor of a different spectral sensitivity. So if I'm correct, the SQM meter is measuring everything in the V band, or maybe it's just some sort of an instrumental band. I'm not an expert on this, but the GMN camera definitely has a much different spectral sensitivity than that. So there might be what's called usually a color term, which is a fixed correction between the two. So if we can at least normalize the methods that are used to estimate the linear magnitudes. For example, if the SQM is measuring it at a certain signal to noise ratio and measuring it in this band, and we have a color term that we can apply between each, then we can have a good objective way to comparing the limiting magnitude estimates between these two sensors. So I think that's amazing work, and that's something that what Gene has done is a good first step into a very interesting discussion. And the fact that we have the infrastructures here, and then the question is, how do we get useful data out of the current infrastructure? And in my view, the best way forward would be to treat the cameras as an any astronomical instrument. So take all the calibrations, take the dark frames, subtract the backgrounds, try to create some sort of a flat. So the RMS does create a flat, but it assumes that there is no sky gradient, which works fine. for cameras which are in dark environments and have long lenses, so very small fields of view. However, for our cameras, which are mostly in populated environments where there's a lot of light pollution, you have these big sky gradients, and we have a large field of view. Our flats don't really apply, so that's not really a flat then, and that's something we can't use. After the dark is removed, we would get some sort of an idea of what the quote unquote dark current is. And after that, yes, we can take individual pixels, and because we also have the plate, we can also do the mapping and compute quite literally the magnitude per square degree or magnitude per steradian in the sky, and actually get a mapping of light pollution and sky brightness in an objective way across the field of view. Um, there's also another potential issues that most of our cameras don't really point towards the zenith. Now we do try to take out the effects of vignetting and extinction, but that does not include the effects of light pollution. So ideally, we would have a near field camera which has a dark, a flat, pointing straight up the same field of view as the SQM meter, and only then we'd be able to do some objective comparisons, derive the color term, and then see if we can, in an easy way, adapt other cameras using some sort of even empirical corrections to compute good numbers comparable to what the SQM instrument is producing. These are some of my thoughts regarding this topic. I would love to hear a further discussion. So,
Well, I'd like to, I mean, you're proposing, and rightly so, a rigorous approach to to understanding the relationship between RMS and SQM, but I don't think we're compelled to match up to what the SQM meter is. We just need, I think I'm more interested in a reproducible tool that I can use, that's stable enough that I can use it in my local camera to assess changes, trends, light pollution changes within my local environment. So it's less important to me to have a rigorous calibration than it is to have a stable way, a reproducible way that measures a signal, gives me a signal that I can measure its change over time, whether it's directly connectable to a standardized light measuring device is, at least at the outset, less important, I think.
mhm. Well, if
So
that's the case, then the photometric offset already does that in a sense. That gives you a good relative measure uh, in terms of the sky quality and brightness, because you can see a change. For example, when the moon appears, the
yeah.
photometric offset dips, and
Any more about how that photometric offset is derived?
yes, yep. Oh, in terms of so you're wondering how the
Where does it
measurement
come from?
is
Where's
done.
that?
Oh, where does it come from?
Yeah.
It's actually very simple. And I can even probably just demonstrate it live. So we have to connect pixel intensities to magnitude somehow, right? And we know from the definition of the magnitude what the relationship is between let's see, between linear intensities to magnitudes, and you also need some sort of a 0 point. And mathematically, the relationship is minus 2.5 times logarithm of flux of interest, a flux of interest divided by the reference flux, and that's it. Okay, so how do we then operationalize that? And what is the photometric offset? Well, if you remove that reference flux, we kind of take it out of that logarithmic equation, you just get an extra term an external term, which is the photometric offset. So let me just find one example. Okay, I think I have a nice camera here, and I'm gonna load it up. I'm gonna share my screen here. Okay. Uh, this is here. Okay. There we go. Okay, so we have a star field, it's already calibrated, and then we have a certain star, and what we have here, okay, this one is saturating. So let's find one that's not. For example, this one. Okay, so what kind of information do we have here? So we matched it to a catalog star. We know its magnitude. We want to relate the total intensity, the pixel intensity of this star to the magnitude, the catalog magnitude. So then the first step is to subtract the background and sum up the pixel intensities of the star. So this is done with what's called aperture photometry, right? So that's why we have this annulus with an inner and an outer radius. So in the inner radius, the star pixels are all summed up. And before that's done, the median value, the median pixel value in the outer radius, or shall I say the ring in between the inner and the outer radius, is subtracted from the pixel intensity of every single pixel, right? So that's what's happening when we click on the star here. So then we have a value that SkyFit actually reports. So this is the intensity. So this intensity right here, again, is the sum of all the pixel intensities, but background subtracted. And it also measures the signal to noise ratio. That's a recent addition, which here it's about close to 10. And it says it is not saturated. It also tracks a number of saturated pixels. Okay, now let's pick another one. Okay, this one has some saturated pixels. We're going to ignore that. Okay, let's go here. And we need at least 3. That's the minimum that I set for things start showing up. Okay, now we have 3 selected. And then let's go to the photometry fit graph. And can't really see much here, but you do have 3 points. And this is the photometric fit. So on the x-axis is the uncalibrated magnitude, and on the y-axis is the catalog magnitude. We know what the catalog magnitude is. And as for the uncalibrated magnitude, that is simply the pixel intensity. So this value right here, we take the logarithm of this value and then times minus 2.5. And then we get this uncalibrated magnitude. Again, this all comes from the definition of the magnitude. And then what you end up with is potentially a linear relation between the uncalibrated magnitude and the catalog magnitude. And this line here is a 1-to-1 slope. And the only thing that you have to do then is you have to find just a vertical offset, the intercept that is going to convert the uncalibrated magnitude into the catalog magnitude. So quite literally, this slope here just goes up and down, this line here. And the value that regulates that is this here. So in this case, it's 10.23. This is what we call the photometric offset. So LSP, it's called log sum pixel. We have a sum of pixel intensities. We take the log of that times minus 2.5, again, from definition of the magnitude. And that's how we get this. And if we just keep adding things, stars are going to fall on this line. So let's pick a fainter star. For example, okay, this one might be a bit too faint, but let's say pick something like this. And then pick something, for example, here. And then let's pick something brighter. This one's saturating a bit, and we're actually going to see that in the graph. And then let's pick another one. Let's say this one here. And if we go back to the photometry graph, you're going to see that they all fall on this line very roughly. This one is off and it's actually marked as saturated. So it no longer follows this linear relationship because the sensor started saturating. So, and it's actually excluded from this fit, so it doesn't mess up the fit. Now, there's some corrections that we have to do to this because of lens vignetting and atmospheric extinction, and this is what these other two plots are showing. So the vignetting model is modeled with a drop off, which follows a cosine to the power of 4. As far as I understand, that just comes from optics. It's a theoretical model, and it's pretty good. So, for example, if we just pick something here in the corner, we'll see that it's going to follow that model quite well. So there are two colors here. The red is raw and the blue is corrected for vignetting. So you can see that there's a 0 line here. They all cluster around this line, and then they follow this curved line. The red ones follow this curved line. And that's where the photometric offset comes from. Now, how does that relate to the quality of the sky and some other things? That's a good question. The relationship needs to be established, but this is probably the best objective measure that we have because we can correlate directly to catalog magnitudes and we're measuring the background subtracted intensity of each star.
So, so then the offset is an average over the whole sky then.
Correct. Yes. And that I understand is a problem. Now, we do have a very rudimentary model of the lens with the vignetting model, which takes out that, and we have extinction, which takes out atmospheric extinction only. So it does not include sky glow. So in a case,
Is the extinction correction applied to the offset?
yes, it is. So it corrects. So what this does, it takes the catalog values of the magnitude and then makes them fainter the closer they are to horizon according to the extinction model to produce an apparent value. That's all it does. So again, the big gaping hole in this approach is it does not include the sky glow. However, the sky glow, in my opinion, just contributes to the background, which gets subtracted. Now, it also might drown out some of the light that comes from the star through light scattering and some other effects. So those are some good questions. So the photometric offset measures does not measure the local sky conditions, but it measures the sky conditions. How can I put it? If there's cloud or the sensitivity of the camera changes or the moon comes into the field of view, the photometric offset is going to change.
And you think this is superior to using the field sums because the field sums are not
Background subtracted. Yep.
background subtracted?
Yep. So the field sum
And you don't
sums
think
up.
the background is constant? You don't think it's safe to assume that the background is stable?
I mean, you can.
The instrument noise at the instrument dark current is stable?
It might be, but I also have a suspicion that it changes with temperature. And especially if the camera is outside and we have big temperature swings, you can probably notice big changes in the background noise as well. I mean, one thing that can be done if you want to map the if you want to map how if you want to map the sensitivity and the across the field of view, you can fit the photometric offset per star. So that way you get a photometric offset, for example, for this star here, but then you can track it across the field of view as it moves during the night. And that way, you know you're looking at the same star, And if you normalize it to the average photometric offset across the field, the whole field of view, which gives you some sort of a reference point, this way perhaps you can map the the photometric offset in certain regions of the image, assuming that the background doesn't change. That would be a potential approach.
Would it be possible to uh, look at the faintest star detected in the field and use that as something that might imply the amount of sky glow and or light pollution?
You can, but then that's also again a measure. You get one number for the whole field of view. And the question is whether we want that or we want to map everything across the whole field of view.
Then the other approach I'm thinking about getting into, and I don't know quite how to do this, is to try to run a correlation between let's say the offset value and the field sums value. Is there just do a empirical exploratory look into a correlation coefficient between the offset and the field sums and see what falls out of that.
Yeah, I mean that's one way to do it. Um,
I haven't figured out the technical problem I've had is that I haven't figured out how to read those binary files yet out of
oh,
the yet. So I'll need somebody will have to show me the trick on how to do that.
okay. Yeah, so we have RMS has code which shows you how to do it in Python. Quite easily. It's just a few lines in NumPy. So we can definitely send that over if that's going to be helpful. Um, but see, all of my ideas require some manual work. And what I would like to do is um, connect, or how can I put it? I would like to make manual measurements for all stars across the field of view, and then also get an SNR for each star. And have a value of intensity, have a photometric offset, and have a few more things, again, including the SNR. And then what we can do is we can set a cutoff uh, with SNR. What I mean by this is let's define the limiting magnitude as detection that's going to happen above an SNR of 1, 3, 5, or et cetera, et cetera. And that way, that is a hard objective measure. Unfortunately, that requires us to go in and do a lot of manual measurements and then save this SNR value from SkyFit. I mean, I could make a minor change that SkyFit actually changes that saves all these values in some sort of a CSV file, and you can read from there. And then you're going to end up with a graph if you plot out the SNR versus the magnitude, and then also include a photometric offset. We'll be able to see how that changes across the field of view, and then that is going to set the hard limiting magnitude. So what I mean by this is, imagine if we plot this SNR versus magnitude versus the apparent magnitude that has the extinction applied, and not the catalog magnitude, right? And then uh, you you see where the SNR of 135 is. That converts to a magnitude, and then we can say, okay, that's the limiting magnitude, and then we know what the photometric offset is globally of the whole field of view, and then we can say at this photometric offset, at this SNR, the limiting magnitude is this. And that way we could create a more robust model that takes the measurement uncertainty into account, and the actual noise characteristics of the sensor versus just trying to connect things that might have some other inherent biases.
But operationally, to do this, you're talking about, I mean, for one night of observation, you have to do this for each field for the field of view that you captured at 5 second intervals, right?
So basically what I'm saying is, and let me just pull up the current equation. So what I'm suggesting is we have to update the equation. Where is it? So stellar limiting max. Okay. So this is the current equation that we're using, right? And this is the equation that I derived on by manually looking at the number of stars that I can see in individual star fields, following that Visual Observer's Handbook. And I created an Excel sheet, which I can pull up. Back to, okay, there it is. If only it would open. There it is. So I created an Excel sheet, and essentially for, let's say, one camera, I recorded P0 is the photometric offset. I recorded a stellar limiting magnitude that I determined using the IMO method, and I made a fit. And this number that you see here is the number that's used in the flux code right here. So what I'm suggesting is, instead of doing it by eye, we would actually look at the SNR. And that way we can even say, okay, I want to pick a different SNR and I'm going to get a different definition of the linear magnitude. So we can change the equation depending on the SNR. So I like the equation to have a dependence on SNR, on P0M, and also potentially on full width at half maximum. So for example, I suspect that if your camera is out of focus, the limiting magnitude is also going to be different. And this number is already present in the CalSTARS file. So even here, you can see that I computed the residuals of this fit, and then I broke it out per you see LM minus model, and then I plotted it with full width at half maximum, and you can actually see as the full width of half maximum increases, so does the limiting magnitude. Sorry. Yeah, it's the other way around, but you understand what I mean. So there is also dependence with the focus, which one would naturally assume. So I think we just have to include all of these things in the equations, improve the model, and that way we're going to have an objective way to do it. And the way to do it would be to update this table. Yeah, so look at, make a lot of measurements with SNR. And again, yeah, so you would have to do this on different star fields from different cameras at different values of the photometric offset. So for example, like this HR1 camera has a 16 millimeter lens, so it sees many fainter stars, and P0 here is 12.5. On the other hand, this one here is an all-sky camera, which GMN doesn't really use all-sky cameras, but in this case, there was an experimental camera that was running for some time, and it has a photometric offset which is much lower, which means its sensitivity is also much lower, which was the case. And if you can see that the limiting stellar magnitude here was 3.6 compared to about 6 for 4 millimeter cameras, and 16 millimeter cameras had a limiting magnitude at around 8. So that's the rough idea. Covered the range of lenses, quantify the SNR, quantify the full width of half maximum to take out the focus effects, and get a better model.
So can I ask you on your SNR, is that just calculating the ratio of the area in the ring around the star, like you were showing us earlier?
Yeah, so essentially it takes the sum of the signal that's inside, and then it estimates the standard deviation of the noise, the standard deviation of the background in that outer ring, and then it computes the SNR using the standard, I think it's called a CCD equation.
One thing that I think you might have an issue with is if the light has more infrared component in it, then it can penetrate down in the silicon and it spreads out in those outer pixels around that center.
Yeah,
It won't be too obvious to you, but it's happening.
it's true.
And so you'll have a different SNR depending on the spectral characteristic of the star.
Yeah, yeah, it's perfectly possible. I mean, that's something that we probably won't take into account initially. But the general advice is that you adjust the annulus according to what you can see. But it's a point well taken.
And then from what I've seen, the moon and headlights from cars that are on a highway but not too far away, and stray light scattering around, all kind of migrates through the night. And so it's a constant update requirement, I think.
Yeah. So Luke, go ahead.
So when you did the fit for the on the table, you showed it. How does extension takes? How is that taken into account?
Sorry, extinction?
Yeah,
Oh, it's not.
because there's no pointing elevation correction, or how does that work?
Yes. So, uh, what I've done here is so you have the P0M, which is derived globally, and that takes out the extinction, right? So this fit was made on stars that have been corrected for extinction already, right? And this number here is the catalog limiting stellar magnitude. So this you can think about it as already extinction corrected,
Oh,
and
the
this is
extension. Okay.
also,
Okay.
yeah. So both of these are normalized in the same quote unquote system. I might get a student to do this work the next couple of weeks, and I'll keep everyone posted. But it's an interesting problem, that's for sure. And it might unlock some new capabilities that we can apply, and it can improve our predictions of how many stars we have in the field of view, and a few other things. Now, one thing that's interesting is that it's not here in this table. I wonder if it's on the second sheet. I don't know. I have no clue what this is. I also put the some data from a non-GMN camera that had a photometric 0 point of around 16 or so. So the stellar limiting magnitude was maybe around 11 or 12, and it still followed this line. So the implication is we actually might derive some sort of a general model for CCD/CMOS sensors in general, where anyone can just measure their photometric offset, plug it into the equation, and get a limiting magnitude out, which I think would be quite exciting. Maybe there already is such a thing that I'm not aware of. Maybe there's another way of getting at this. Maybe one could actually do some simulations of sensors, et cetera, et cetera. But okay, Jamie, go ahead.
I come from an age of photographic film,
Mhm.
and I studied under the team at Blackford Hill Observatory in Edinburgh, who were doing pioneering work in astrometry. And one of the things, if you're working with film images, with nonlinearity being a problem, is you have to find ways of correlating that nonlinearity with really accurate photometric magnitude scales. And they actually developed a piece of electronic equipment called a Becker iris photometer. And what that did was it adjusted the size of the iris to a point where the light that was coming through, this is using a photographic negative, the light coming through that iris, through the middle aperture, was set at a constant value. So as you moved it over the star images, I actually used this piece of equipment all those years ago. The iris would have a mechanism that it slid in and out. It made a little buzzing noise until it matched the light output. Now, it struck me that if you have a fireball which saturates, then a way of creating a scale for determining the magnitude of that image would be simply to have an iris much larger than the fireball image, but plot within that all the pixels that were, say, brighter than half the difference between saturated and background. And so that would give you a constantly varying number of pixels and a level of each pixel that you could create a constantly varying readout for the intensity of that fireball image. And I think if you were to attempt that type of method, it would borrow knowledge from those old film days, and it would mean that effectively you never had such a thing as saturation. You would be working with a non-linear scale. But when I use that iris for bright fireballs, you find a stepping effect unless you use it very precisely. And if you used a method where you had a certain fixed pixel value, if it went above, let's say you had 256 levels, let's say 40 was background, then you could set it at, say, 160, and that would give you wouldn't have to worry about varying the size of your iris. The iris would be bigger than all the possible sizes of the fireball image, and it would just constantly adjust automatically and give you a value which you could then equate to some kind of curve fit to that inevitably non-linear scale. So that's just my 2 cents worth for a possible approach.
Mm-hmm. For correcting saturated fireball imagery, correct?
Yes, that's right.
Yeah. So that's actually something that, if I understand correctly, something that we already kind of do, where we try to measure the radius of the fireball that we see in the video frame. Do I understand that correctly? Or
Yes, you're measuring the radius where
radius?
there's pixels that are above background.
Yeah.
But you set a level for that, and you
Mm-hmm.
just say everything below that level doesn't count, and everything above that level, you count up those pixel values and add them all up, just as you do normally.
Yeah.
In effect, instead of having a round iris,
Mm-hmm.
you would have this irregular
Whatever shape.
blob
Mm-hmm.
that was just determined by the light level of each pixel.
So that's a great suggestion. And we already have a similar approach where we measure this kind of radius, but not on a rigorous pixel cutoff scale. There are a couple of wrinkles though. And the wrinkle is that sometimes the sky around the fireball, you get this indirect light coming in, and the whole sky increases in brightness. So you don't just see a blob increasing in size, you also get scattered light from across the sky, depending on the atmospheric conditions and the humidity also go in and raising this level. So it can be quite difficult to determine where the edge of the fireball is, and especially if there are some reflections in the optics, that can become more complicated. So we've adapted uh, a similar method which is applied manually. But that is a very interesting idea, which I guess we can probably try. And
Even if you didn't achieve perfect photometry, one thing it would certainly do would be to automate the smoothness with which you establish the light curve. You'd be able to see features in the light curve that were independent of manual adjustments of the iris aperture.
That's a great idea. Now, in terms of that nonlinear curve, now that's something that Damir has been chasing for a while, but then he switched to stellar photometry. Um, one one thing that one way to approach it would be, okay, you use the regular camera and then you observe the moon or some bright stars or some planets that saturated and you make that connection. The problem is you have this big gap between the brightest stars and the planets and the moon. So we realized that you don't really have to do that. The only thing that you have to do is to uh, map out the space um, in the this uncalibrated magnitude space and not the raw magnitude space. So that way you can take, for example, a 16 millimeter lens and then point it to Jupiter or Sirius or Vegas and Bright Star, have it saturate massively, and then on sensor is going to have the same effect as having a wide field lens and a bright fireball. And that's how you can map out the response of the sensor to a huge amount of light. You just kind of quote unquote trick it using a different kind of lens. This is something that I hope that Dummer would give us an update on, but I guess we're going to leave it for some other time. And we started thinking about this work in the saturation correction is after the meteorite fall in New Zealand when we didn't have a single source of unsaturated imagery, and yet just by looking at it, just from my experience, I can tell, you know what, this is like magnitude like -10. It doesn't look like -8, doesn't look like -12. -12 is way too bright, -8 is way too small. It's got to be -10. So can we get a method that can measure magnitudes within, plus or minus half a magnitude. We don't need much more than that to get some average estimate on the estimate of the initial mass of the body. And Dummer got something that's close to that. So yeah, we have the curve, and I think probably the best thing to do would be just to get in touch with Dummer and see what he says, so we can push this work forward.
And the other thing is the magnitude determined in just by using the FF files is inevitably lower for slow fireballs than if you're using the full FR data.
Yep. Absolutely, yes. The FF files and photometry should not be used in the same sentence. They were not designed for that.
But in the automatic data reduction pipeline, I don't think there's any use made of the FR files. Is that something that's possible to create in the future?
My suggestion would be that if we go anywhere in the future, it would be to switch processing to full video files instead of trying to fix the FR files and the FF files. I mean, it would be possible to make the detector fast enough to extract raw video frames of all detections, not just bright fireballs, and then use that as a basis for good photometry. So yeah, I mean it's a great idea. If it was a priority and we had time, it would be we would do it.
There might be some way of cobbling it so that you can make it a bit towards that accuracy without actually for example, one thing would be to add up several of the one frame snapshots in the FR file. You could compensate for the effect of a slow fireball that way. Just saying it's going so slowly that it's having to spread those pixels out too thinly. But if you calculated the speed across the frame, you could say, well, for that speed of movement, you just, instead of using just one frame, you could use 2 or 3 or 4 or 4.3 frames worth of pixels to get the light value.
It does make sense. So okay, so Luke, you have a question or a comment. Go ahead.
Yeah. And since Jamie is here, I was wondering what he thought of this issue. I'm trying to share my screen. Let's see here. So even if we get perfect photometry, there's another wrinkle. You guys see my screen here?
Yep.
So,
You're good.
Here I've got two. I was testing different sensors. So I've got an IMX 291 and I've got an IMX 662. They're recording the same event, and there are two events. There's what appears to be a very faint satellite moving slowly, and a very fast, dim meteor. So you would expect that the more light-sensitive camera would see both events. But no, the very light-sensitive camera didn't see the faint meteor, but saw the satellite, versus the IMX 291 being a little less sensitive, didn't see the satellite, but saw the very fast transient meteor. So even
yes, I saw your excellent comparison of the different cameras. The the IMX 291, it loses thready, thin images. You can have a meteor that's almost faded out, and instead of just fading out gracefully, it just seems to completely lose the trail altogether. Whereas what's the better camera? Is it the six something?
Yeah,
the
The 662, yeah.
660
That
doesn't see the meteor.
From my experience, when I look at the 662 camera and when I look at the 291, the 662 looks too nice. It looks too good. It's like so many stars everywhere, and it's too polished. While when you actually work with science grade cameras with no compression, no processing, with nothing, you put them on the sky and you look at the data, it's like, "Ugh, doesn't really look that good." But in reality, that is how data is, right? It doesn't have any it has a lot of noise and all things that these cameras are trying to suppress because they have to feed all this data through a very narrow pipe, and they have to go
Right.
through the 264 compression, right? So that's where a lot of it gets lost. If we were able to hook up directly to the sensor and not have the 264 compression, you would probably see a lot of noise that just gets eaten away by the noise compression, noise suppression.
Don't get me started on the Nikon DSLR and the way it pre-processes the pixels of supposedly raw images. But it's not as bad as the Sony A7, which had the disappearing star problem.
Yep. And what's the weird thing is that we have been trying to buy a science grade or kind of a machine vision or industrial grade version of the 291, of the 307, of all of these cameras that we're using. And every time you try one, the sensitivity doesn't come even close. Even if you crank up the gain all the way up, if I don't know why, they just don't make them that way, that sensitivity matters. And we would love to have a science grade camera without all the, 264 compression issues and these noise issues. It would be amazing, but they don't make them like that. I'm not sure why.
Can I
Bob,
make a comment
too
about
small.
the issue between the two cameras? They're clocking this data out at 25 frames per second. Could you just have an issue there that you happen to miss that because it wasn't visibly switching between the 25 or between frames?
So they're both
Clocking badly.
exposing each frame for 40 microseconds, so it's supposedly gapless. And I have many, many more examples of the same phenomenon. So it wasn't just a coincidence. It's like a consistent issue between those two types of sensors.
Okay.
just a crazy compression, I guess, which is too bad, right? And there's no way to really turn it off, which it's one of the, I guess, elements in assessing the quality of the instrument and understanding how many meteors are lost, which is a big issue. Okay. Does anyone have any other topics for discussion? Pete.
Yeah, I wondered if you wanted to discuss the issue that I raised in the earlier session and my uneasiness about the number of our cameras that are running an out-of-date operating system.
Yep.
I kind of looked at the numbers again, and of the Pi 4, all the Pi 4s together were 265 cameras. I just eyeballed it and said, well, I'm betting that 550 of those are running Buster because Bullseye was released so much more recently. If that's the case, then about 70% of our cameras are running an out-of-date operating system that's no longer receiving security patches or other maintenance.
Yep.
What do you think about that? I guess I hesitate to raise this issue on the forum and cause a lot of unnecessary problems. I don't want to rock the boat.
Yep.
But I'm just wondering, I mean, that sounds like potentially a huge liability should some sort of exploit somehow get into all of these cameras. So I'm kind of wondering what people think about that and how it would be best to proceed, if at all.
Well, the good news is that most cameras can't communicate with each other. So if there was an exploit that would try to, take the whole network down, most of them are behind a local network where they're not really aware of each other, and they can only communicate to the server, which has very strong protections and puts limitations of what the cameras can do. They can just upload into their protected little folder. And in fact, every time they connect to the server, there's a little virtual server that pops up for that camera just for that session and uploads into a little sandboxed area that exists for just that session, and then it disappears when they log off. So that's kind of our approach to security. Maybe it has some issues, perhaps, but in terms of whether people should be concerned if something can attack their camera on the local network, my answer would be we need to keep all the systems updated all the time. The question is whether that's feasible and whether people on their local networks are running some devices that are no longer being updated. I mean, even today, I think I've seen a few people share screens and they're still running, Windows 7 or some other operating systems that are not being supported. So it really depends on how comfortable you are with your security and what kind of environment you're operating in. I mean, if the camera was installed at a school or some other place and it's running an old system, 100% it should be updated. If it's your local environment with limited exposure to the internet, maybe the requirements would be more relaxed. But that's just my opinion. Maybe an actual security professional or someone who has more experience can. I'd love to hear from them. No one's going to risk it. So yeah. So my suggestion would be to write an email to the group, and we can say this operating system is out of date. It is strongly recommended that you reflash it and update it with the latest image. I wouldn't really go beyond that. Yeah.
Okay. And then I think the next part of that question becomes, which image do we recommend that they update? I mean, where do we recommend they go? Because the only problem I've seen with the bullseye image, and it's shared by the bookworm image, is that something is partly broken in the file manager, whereby a simple copy and paste information that works every time on Buster, most of the time screws up on the newer versions. And the workaround is, oh, you can't paste into this window? Let me start another one and paste into that instead, and then it works. And I don't know whether Raspberry Pi organization is even willing to acknowledge that this problem exists. And it may not impact 95% of our users anyway.
Yep.
So I guess those are some other considerations that before we raise an issue like this, well, we should have a really good, solid plan for what we recommend that people do.
Another question is, how long are those alternatives OSs going to be supported? Are they the LTS releases or not?
Well, as we're speaking strictly of Raspberry Pi, the issue is that the Bullseye release will move into the status that the Buster has now the next time that Raspberry Pi releases the next version. In other words, they only keep the current one and the one before.
Yeah, yeah.
And so we could guess that the Bullseye image may only be good for another 2 years.
Yeah.
If their release cycle continues at the pace it's been going for a considerable period of time.
Yeah. Yeah.
So that means it's going to be a reoccurring problem.
Yeah.
And I'm not that worried about it. I just wanted to bring it to the forefront so that some other people were aware of it. Because to be honest, we don't even have a mechanism to know how many are running Buster versus the other ones. We can only guess by when they were opened up. And I know that there's reticence about collecting statistics on what operating system is being run because it may open security holes and for people to know that there may be vulnerable systems. So in some sense, maybe the less said, the better until we really decide we must move forward.
So does it make sense to recommend something to people that will again go out of date at some close time in the future? I mean, even if it's a year or two, I think asking people to reflash that many number of cameras is, I mean, at some point, the SD card is going to die on its own.
Yeah.
So they're going to reflash naturally. Whether that happens in 6 months, a year or two, I mean, that it's going to happen, right?
Well, the other way to look at it is, when did the Pi 3s stop being the go-to thing? I mean, that's the other thing. The hardware is constantly revising. Anybody starting out in GMN today should buy a Pi 5.
Yeah.
No question of that, just because it opens things to the future. So maybe it's not that big an issue. We are, in a sense, already kind of obsoleting operating systems because if you look on the wiki, you really have to struggle to find a Buster image. It's been deprecated in the sense that it's no longer linked. And then maybe that's the only mechanism we need.
Yeah, I mean, things are going to keep changing, and I feel that we will only have ever three generations of Pis total. So we're retiring to Pi 3 now. And I have a feeling that when the Pi 6 or whatever comes out in a few years, most of the Pi 4s are also going to be in the retirement stage, and we're slowly going to probably be less than 50% of the network as they get replaced. So, I mean, my message probably at this point would be just leave it to SD card failures, and then they're going to be replaced. I think that's a good strategy. It's going to happen at some point. I understand there's some people who are running SSDs, but yeah. it's a it's a problem when you're running a distributed network that doesn't really have very strong central control. On one end, it's good. People have their, how can I put it, data control and system control. But on the other hand, keeping things in check and yeah, I mean, at some point, we can say that camera operators are responsible for their security and understanding the implications of the system that they're running. We can do as best a job that we can, but unless we have, a factor of 10 higher resources that we can directly engage with every single one and directly control each camera and secure each camera, it's never going to happen, right? Yeah.
And the other way to look at it is the overall risk to our data collection is very low.
For sure. Like one camera might go down. So what?
Mm-hmm. Yeah.
Yeah. Reflash the card and off you go. Yeah.
Okay.
Awesome. That's a good question. There's also another item, and I think I already kind of started topic, and that's dark flight modeling. So a couple of was it a months ago or maybe last year, I wrote my own library for dark flight from scratch, and it works. It produces good results. It's written purely in Python. It's easy to install. It's reasonably well documented, but the only issue I have with it is that I don't know if I should trust it. Sometimes it produces good results and compares well to different other codes, and sometimes it produces something else. And I'm not sure if that's because the code is more advanced than others, or there's an actual problem, or there's an actual bug. In fact, I've fixed some important bugs as compared to some other models, which were using an integration time step, which is too big, which caused some terrible numerical issues. But that's something, if someone is willing to play with it, I'd be happy to give them access and they can just run it, and maybe if you're crazy enough to look at the math, feel free to do it, and see what you can get. And I already shared with Jamie, I believe. So he has access to it, so he can use it for his own purposes. But I do not want to share it more widely before it's fully validated that it's working fine. That's something I'm just kind of throwing out there. But in
That's a
general,
privilege, Dennis.
yeah.
And I'll certainly have a good tinker with running it through Fireball results. There's a couple of rocks even near my house in Scotland that probably are about the size of a prune.
Okay.
And I don't mind trekking in the hills just in the off chance that I might bump into one.
That's awesome. Yeah, I mean, the general idea is that we also want all the networks to have full control and to full independence of their own searches and recovery. I just don't want to distribute something that I still have suspicions about. And before it's fully validated, I want to compare it to some other codes that I have that I can't share. And then only then, if things matched, I'm happy to send the results over. Okay. Does anyone else have any other contributions?
Is there a trip point that shows or comes up somewhere that says you may have a rock that hit the ground, or that's just something we have to manually analyze and figure out on our own?
Sorry, is there a
Is there a meteor that could have the fireball that could have made it to the ground, went dark and made it to the ground?
you have okay. So that is a question of what we call terminal mass analysis. So that's a great question. And a lot of people have it's the tools that we have are a bit, I wouldn't say tricky to use, but it's a tricky problem. Um, the way we usually do it is by making sure that we have the end of the fireball observed quite well. So let's say the last couple of kilometers before dark flight begins. And we have the fireball observed all the way down to about 3 to 2.5 kilometers a second. And that is what we call the ablation limit. So below that speed, ablation doesn't occur anymore, and the dark flight starts. So it very quickly decelerates and then goes subsonic. Um, and there is a set of equations that can be applied to this last portion, which assume that the mass loss basically stopped, and the only thing that's causing deceleration is atmospheric drag. And atmospheric drag can be explained by a set of very simple differential equations. And what you can do is you can fit that equation to our data. Now, there's actually a trick that you can use that uh, lets you derive the mass by assuming a density. So the only thing you need to do is you need to just need to get an estimate of the deceleration at the end. And once you have that, you need to assume a density. And with those things in hand, you can compute the mass of the object. Of course, assuming the shape and a few other things, but everything's a sphere. So that's a simple assumption to make. And after that, you get an estimate of a mass. And I'm just going to pull up the estimate that we computed for that New Zealand meteorite. So let me see, that was 2024 0313. And then trajectory. No, that's not the one. Uh, I won't have to redo it. This might be here. Oh, okay, there we go. Let me just quickly share my screen. Okay, it's right here. So what you're seeing here is a plot of velocity and height on the left. And then on the right-hand side is just the last, I believe, 3 kilometers. And what we do here is we fit a line through these velocity measurements, and the slope gives us the deceleration. And then with the estimate of deceleration and the uncertainty in deceleration, and assuming the density, so this rho m is the meteor density of about 3,500 kilograms per cubic meter. And there's also another parameter called gamma A, which is a product of the drag coefficient and what's called the shape factor. A shape factor of about 1.21 means that it's a sphere, and gamma simply says how much of the incoming air is transferred into the deceleration of the meteoroid. So imagine you have an object that's flying very fast, and you're going to start seeing a shock formed around the front, and this shock screens some of the incoming air, and not all the air that comes that's supposed to come into contact with the body actually does and contributes to deceleration and actually gets routed around. The shock kind of deflects it. And this parameter usually varies between zero point 0.5 to about 0.7. And that's something that needs to be assumed. And once you have those values, you can compute the dynamic mass. And in this particular case, it was about 1 kilogram. That was the nominal value. And then what we do is we estimate this dynamic mass at the middle, and then we actually run a numerical ablation model to determine what this mass would be at the end of at the ablation limit of about 3 kilometers a second. So you can see the difference here is maybe about 50 grams. It's not too much, but the estimate here was about 950 grams. And I believe that the meteorite was, when it was found, it was about 800 grams or so, maybe a bit more. Is it 850? Maybe Marshall can, if he's still here, he can.
Yeah, it was 810, so
Yeah.
pretty close.
Pretty
Yeah.
close, I mean, well within the uncertainty bounds. The uncertainty bounds were about between 500 grams and 2 kilograms. So you can see that the uncertainty bounds are more logarithmic than linear, just because of the nature of the model, right? So this is one way of doing it when you have good measurements at the end, and this is where GMN cameras excel. So they see fireballs decelerating all the way at the end, and at this stage they become quite faint. So this is like zeroth magnitude, or this last point might be like third magnitude, very very faint. And that's something that you can get with other less sensitive, especially all sky cameras. So in that case, what they have to do is they have to fit a model to the whole fireball, and only then they get some sort of an estimate of that at the end. So this is the trajectory of our fireball of interest, and I'm just gonna quickly run that model just to show people how that works. And that's something that was developed by the Australian group. Uh, okay, so this is RMS. I don't need that. I need to hook up to so I think it's in utils in the alpha beta. And this formulation fits a model. I don't even know what kind of what parameters this takes, but this formulation fits a model that's derived on what's called single body ablation theory. So imagine a fireball does not fragment, which of course doesn't happen in reality, but it does give a rough estimate of the mass at the end. So if you run this, you'll see that the fit is going to be a bit different. It actually fits the whole fireball, fits the whole curve at the end, fits the whole curve, and then gives an estimate of the final mass. And that comes directly from the equations. And the final mass really depends on some shape parameters and a few other things, but these are the results here. Please do not read into the initial mass estimates. As you can see here, they're completely wrong. There's no way this object was like 1.5 kilograms, but the final mass estimate is actually quite close. So about 0.9 kilograms to about 0.44 kilograms using this method. There's also another way of looking at this is that you can um, plot it up in this space. And the two parameters that are being fit, they're called alpha and beta. One is called the ballistic parameter, and I think the other one is called the mass loss parameter. They don't mean much on their own. However, what you can do is you can plot up these curves, telling you what the masses of the meteorites are. So these are the 50-gram masses, and these are 1 kilogram masses. So in this particular case, this point here indicates that the estimate was around close to this kind of one kilogram limit, 1 kilogram limit right here. So these are the two different tools that we use. So again, the first tool that I showed, that tool is used when we have good observations of the deceleration at the end. This alpha beta tool is used when we don't have that, but we have to use the deceleration of the whole fireball to get at the final mass. And yeah.
And it's just a follow-up question. So when you estimate that strewn zone, it's basically then a series of dots on the map, for different estimated final mass.
Yep.
So what are those? Are those dots their individual simulations for different variations of the parameters, or?
Yeah, for sure. So I'm gonna open one KML file, and I'm gonna show you what's happening and how the model works. And again, I'm gonna use the same meteorite file for this. So
I'm thinking through our case in the Gambia, where
Yep.
both you and Hadrian were assuming a very similar ablation and a very similar final mass.
Yep.
Yeah. But so I'm assuming that Hadrian would be using essentially the same methods. So
I know, yeah, the same equation. I mean, I fully agree. I don't fully understand where the difference is. Again, this is why I'm not fully trusting that dark flight model that I'm currently using.
No.
That needs to be validated. But who knows? So you asked about the different points. So what happens is that this is here the begin point, the terminal point at the height of so this is 22.1 kilometers. That was for this fireball, and we have some latitude and longitude, and you can see time is 0. And then equations are integrated, and the wind field that every time step is evaluated and applied to the rock, and that takes it to one side or the other. So you can see here how the winds influence the path. And we only here plot the fall of the nominal solution. However, what you're seeing here on the ground is a distribution of all we call Monte Carlo realizations. So all the different possibilities. So this is sampled from the uncertainties of pointing and speed and azimuth and position. So all of these possibilities are sampled from those probability models, and the whole propagation is done individually for every single one. It's just not being shown. So the whole like path that you see, and for every point on the ground, and it's just broken up by mass. So what we found is the best way to do it is to take every half dex of mass. So what I mean by this is you sample it at 500 grams, and then a kilogram, and then half a kilo, then 500 grams, a kilogram, half a kilogram, 2 kilograms, 5, 10, 15, 2, et cetera, et cetera. And that's how you get this kind of a equal separation almost in masses. So what these points are telling you that for one particular mass, so for example, in this case, let's say for 1 kilogram, we go to Monte Carlo here, turn everything off, and we only keep 1 kilogram. Oh, these are some, I already have it turned on here. That's not it. Okay, I better turn everything off that I have here. Okay, all temporary places. There we go. And then I only turn it on for 1 kilogram. Oh, it's not in temporary places. Where is it? Okay, there we go. If I only turn on 1 kilogram, this is where you're going to see. So this is statistically the possible distribution where you can find the meteorite that is 1 kilogram in mass using known uncertainties. So so individual points are of course not individual meteorites. They're just indicating the area, the uncertainty area, the uncertainty region. That's all it is. So anywhere in here, there's a good possibility you can find it. Of course, the probability is higher closer to the middle of the probability field.
That's assuming some sort of wind drift as part of.
Yep.
As part of that. Yeah.
Yeah. So in this particular case, I think I can even the atmosphere model is here, and I have a plot like this, which shows you the pressure, the temperature, the wind speed, the wind direction, air density, and the speed of sound, and all of these things are taken into the model. Of course, the most important thing is the wind speed and the wind direction, and this is what's applied to the meteorite.
That data is available from Bureau of Meteorology or sort of reliable sources. Is it how much uncertainty is there in the wind speed and the wind direction?
That came from Invercargill, which is what's that, Marshall, 150 k's south.
Yeah. So usually we use yeah, the radiosonde measurements that are available on the University of Wyoming's website, and I think NOAA also has them in a slightly different format. But the best way to do it would be to use an atmospheric model. And that's what Hadrian is doing. So they have a supercomputer and they have this model installed and they download the data from all of the radiosondes across the world or in the area of interest, and they fit the model to the data and then they interpolate. And you have the model is a bunch of equations, and then you say, okay, I have a measurement here at this time, I have a measurement here at this time, and then it does the fit, and then they sample the model at the right place at the right time of the fall. And that takes care of other things. So the model also uses not just the wind field data, but also uses like tropospheric temperature observations and many other things. So it should, in theory, be much more accurate than just the individual radiosonde measurements, which can be taken from far away, or they can be also distant in time. Well, the model should be much more accurate. Now, in theory, one thing that I found is, for example, for 2023 CX1, which fell in Normandy, if I used the measurements from across the channel that were taken not that far away, maybe 100 kilometers away, roughly at the same time, they fit perfectly. But the model winds take the meteorites to one side. Don't ask me why, don't ask me how. Not an atmospheric scientist. I'm just interpreting the results that I get.
Dennis, that some of that data you just showed us about Takapo, did it? Because I asked Jamie to have another look at it because I revisited the search site to see if there's some smaller pieces. We only had a sort of 3-hour search with a small group of us and didn't find anything. Jamie said, I don't think there's any other bits, and it's just that the one mass. But if you don't look, you won't find.
Yeah,
we didn't find anything. But does that data you showed us fairly well say convincingly that it was just a one mass?
Well, actually, in the video, we did see a smaller fragment potentially, and I did estimate that it's probably around, is it 250 grams? Let me see. No, I forget.
Yes, Jesse State seems to be of the same opinion that there was a smaller mass broke off just before the end.
It's 250. Yes, exactly. And you can see it in the video, but it's not 250. It's around maybe about 50 grams or smaller. And I do have a simulation for that. So I can share my screen. And we did discuss this. The problem is that the uncertainty region is high and it's on the other side of the river. So this is where the meteorite was found up here. And this is where the small piece might be. And I think that the initial discussion was that this was private land and there were some other potential issues here. So I'm not sure that if a search has ever been mounted there, and also the fact that the search area is, I mean, it can be 50 grams, but it can be as small as 10. So the length of this is about 4 kilometers, and the width is around 2. I'm not sure how searchable this is, especially for a rock that small. So 50 grams, we're looking at something that's very small.
It's Jamie's big prune, isn't it? I know the landscape pretty well now. I wouldn't be going there to look for 50-gram meteorite.
Yeah. I think that's how the initial decision was made. And there's also another issue is that with the smaller rocks, so the wind was quite strong here, and the smaller rocks are more influenced by the wind. So if you have a tiny uncertainty in the wind, they're going to be amplified for smaller rocks, right? So if you see where it started, so imagine that the rocks were just going straight, and if it was just going straight, then it would end up somewhere down here in this area. But the wind took them so far away to one side as compared to the bigger rocks. So that's why sometimes if I see that the wind is strong, we don't really send people to look for smaller rocks. But if the wind is reasonable, Actually, the greatest chance to find something is to look for a lot of small rocks, especially if you can see a strong fragmentation point. In this particular case, there wasn't really a fragmentation point. It looked quite smooth with no pronounced fragmentations. So yeah, for one piece or maybe another very small one across the river. And that's why we didn't make a decision to go for it.
Look, very useful just hearing you talk about this, Denny, because I think we've got enough relationship with Andy and Hadrian to sort of work through, you know, work through the issue we had at Nagambi, you know, and my reason for going out searching was I reckon if we actually found something on the ground, it would ground truth either of those models, and we'd be a lot further forward, not just for Nagambi, because I think it's just an ordinary chondrite anyway, so it's not nothing special as a meteorite. But if we actually establish something on the ground, it would provide some confidence in either of the two modeling approaches. So it's nice to understand what you're doing, and you know, when Andy and Hadrian are back from leave, we'll sit down and you know, maybe even rework some of this data. But I mean, Hadrian's going to be using essentially the same methods, I would have thought, Dennis. There's nothing, you know, there's nothing too different in what he would do and you would do. So I'm not trying to put you on the spot, just trying to
No, I mean,
understand it.
it's yeah, I mean, it's absolutely the same method. Like the equations that we use are they're super simple, right? It's not the problem is not the equations, it's just the everything around it, right? So the you know the fireball speed at the end, the azimuth, and the winds. The winds are the really the hardest thing to pin down because you know there's not much measurements, and also the shape and the mass. So you
Yeah.
put all these things together, even though the model itself is very simple, it can be quite challenging
Yeah.
to get a good answer. Yeah. Unfortunately.
Yeah, good discussion. I understand it a lot better now. So
Yeah,
people
no.
are asking me questions about the individual points, what that meant, and I thought it was something like you explained, you know, but I
Yeah,
understand
yeah.
it much better now. It's good.
Yeah, I mean, ideally, we would upgrade the plotting software so it plots it as some sort of kind of a fuzzy probability field. And I understand it, you know, some people see that as like, oh, these are individual meteorites. I just have to go there and pick it up. It's like, no, 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 no. If only.
No, no.
Yeah. Good. Any other comments?
I may have missed the discussion about the wind, but for the contrail, we use the ERA5, which is a reanalysis model. The winds should be pretty good in that model, in that from that source.
We actually we tried using it a few times and it was okay. But also keep in mind that these winds, we're not talking about, you know, tropospheric winds. We're talking about winds that, you know, from, well, starting the stratosphere and then down, starting at 30 kilometers or so. And then,
okay.
Yeah, yeah, that's the problem. Very, very few measurements there. Okay. Any other comments here?
The only thing I could suggest is rather than showing the individual circles that people mistakenly assume are individual fragments, would be to portray it as like shaded concentric circles of some sort. So you're conveying more the notion of probability of something being there. But that's more complicated to display. So
yeah. Yeah, the problem with the, you know, so every single point is a Monte Carlo run, and then you're assuming that you have perfect sampling, and based on that sampling, you can derive as kind of a second order product with some sort of contours or something. But I like to look at the raw products and then make an interpretation. And that's why when we distribute these things for public consumption, we don't even show these individual points. We just go into Google Earth, and then I take that polygon marker and I just kind of shade the big area around it, and I say, okay, this is where the probability zone is. And that way there's no confusion. that includes different masses, different shapes, and everything, and people don't have to look at these individual points. It's the best way to do it.
Just, I mean, a comment from my sort of uneducated view, or just looking at this from afar. Marshall and the New Zealand team, they had a much heavier meteorite in the first place, and they had probably a more or better wind conditions or lower wind conditions. So the confidence in the strewn zone would be a lot greater than a 100-gram meteorite with not so favorable wind conditions in Ngambie. Is that a fair comment or?
Absolutely. Yes. So think about it as kind of compounding probabilities, right? You start with, I'm going to find this rock. There's a 100% probability. And then you add, oh, but the winds were not good. You slice off 50%. The terrain is terrible. You slice off another, 90%, depending. I mean, if the terrain is really bad, then that's where most of your efficiency goes, right? And then you just compound it and you get down to, if you're lucky, you're down to 10, 20% that you're actually going to find it. And that's if you're lucky. Otherwise, I'd say most of the terrain disqualifies almost all meteorite falls from even being searchable. Yeah. That's the major problem.
And I know the curtain seam, that's why they tend to focus on the Nullarbor and Little Desert and, nice red sands where you can find things. So, yeah.
Yeah. I mean, so for example, in the UK, when Winchcombe happened, so that was still in February. The grass was low. There wasn't really much vegetation, and they went out and they found it. It was really easy to find. It was great. And then I think it was in April, they had another one, which is even more promising, and they were all very souped up. They had a team. They went out, and of course, at that point, the grass was knee high, and then they couldn't find anything. They spent, I think, 3 or 4 days searching with a big team, but you just can't see anything through grass that tall. So there's a sweet spot. There's a definite sweet spot when you can find stuff, or they fall on some really unusual terrain, like this case where you don't really get meteorites falling on dry riverbeds or areas like that. It's very lucky. Now, of course, in Western Australia, where Hadrian is, I mean, you're looking for a black rock on a bright orange desert floor. Can't do better than that.
Yeah, that's right.
There's nothing out there except, there's just no. Now, Arizona, on the other hand, even though it's a desert, it does have some dark rocks in the desert. And Luke can testify to such an experience where he last year he went on a meteorite hunt, and it was every rock was a black rock. So either they were all meteorites or
Very good. Very nice.
We found a few rattlesnakes.
Yeah, lots of basalt.
Yep.
It could have been a lot of meteorites there.
Oh, yeah.
Even this one, I was like, is that one? I guess it wasn't.
Nope.
They developed what's called desert varnish that looks like a fusion crust. Yeah.
Yeah. If it was me, I would have turned back and just went home the moment I saw the rocks. I wouldn't even try.
Time to get the magnets out.
2 days there.
Another example of an impossible search area was the one that landed in the Albuquerque metro area. And I thought, well, we can walk the streets. Most of them in this particular area don't even have sidewalks. So it's a paved road. We can walk the edges of the road, but countless barking dogs, landowners, people in individual homes, going, what are you doing out here? It was impossible. There was just the chance of finding anything was so close to zero that we didn't even try for that particular situation.
You can put out leaflets and tell people to be on the lookout, some strange black rocks in their backyard. That's pretty much it.
Yeah.
Good. Well, we're.
Can I just
Jimmy, go ahead.
Yeah, one more thing about the endpoints of fireballs and the strewn field predictions. If I can just share my screen here.
Should be able to.
Yeah, here we go. Working on the thing I was talking about, but with the KML file for the trajectory KML file, I found that was using a fit in the ECI coordinate frame, which is a straight line, and that's how it got all the azimuth values. But what I did was, I'm afraid I completely rewrote the thing. And instead of that straight line in ECI, I was using the actual geographical coordinates in the output from the trajectory pickle. And so you can actually see on the left side, this is without doing the wind correction, and you can see the evolution of the azimuth towards the end of the path. And you've got azimuth mostly clustered up at just over 30 degrees there. This is the Staffordshire fireball over England last year. And just as you get very near to the end, there's a sudden rapid change of the azimuth up, increasing up by several degrees. But if you do the wind correction, now I'm also doing a thing where I subtract out the gravity so that you've got effectively you're trying to make the path as straight as it possibly can be. And you're seeing this would be as if you're looking at the fireball on ground-based coordinates. You've corrected out the wind effect of the rotation of the Earth. And I've used a Savitsky-Golay smoothing algorithm to compensate for the very choppy nature of the data at the end of the flight. And you can see that the evolution in azimuth and altitude is steady throughout most of the track. But when you get to that region of rich air density, there's a very slight change in azimuth, presumably due to the normal upper stratosphere winds. But notice how the azimuth change on the bottom scale is tiny. And a lot of this azimuth change is because the fireball is tracking across a curved Earth. So it's not actually changing in direction. It's the way you measure the azimuth and elevation. So it's tracking across the Earth. And so the elevation is actually decreasing. But then at the end, the winds take a hold and the elevation increases because it's making the trajectory slightly more shallow. But unless you do the correction, the range in elevation and azimuth is huge. You do the correction and it's extremely tight. So you're getting with this method a very accurate azimuth value at the end of the path. Well, this might be a polynomial fitting anomaly, but you could certainly say it's somewhere between 30.4 and 30.6, which is much more certain in the left-hand plot, where it's swerving quite violently. So just thought I'd throw that one in, since I think what you mentioned a few minutes ago was that you were using the KML trajectory file and that other little table that it prints out as seed coordinates for the position and the elevation and azimuth of the final point in the trajectory.
Yes, so there's actually a separate script that goes in and takes care of the Earth's rotation to compute the actual azimuth. Because if you take it as is, right, you're gonna see these effects. That's something that I haven't mentioned. But it does look from your plots that if you take the initial elevation and the azimuth angle, they're pretty close to the corrected values, if I'm correct. We're talking about fractions of a degree, right?
Yes, yes. You can also look at it in, you can take your altitude azimuth glasses off and put on your RE and deck glasses. And as you would expect in Earth-centered inertial, there's a tiny cluster of RE and deck variation.
Yep.
Just fractions of a fraction of a degree
Mhm.
until the wind takes hold. But if you then do it in wind corrected, that's when you get the evolution of the radiant. Now, that's what you would expect because the radiant is only fixed if you don't muck about with it in the atmosphere. The moment it gets that Earth rotation wind, the radiant, Ari, and Dec are going to instantly start evolving.
Yep. Yep. So essentially, because it slows down enough that there's time for the surface of the Earth kind of slip beneath it and effectively change the direction it's pointing relative to the ground.
Now, this is plotting the mean fitted trajectory rather than the individual data points.
Mhm.
But I think the reason it jiggles about a bit is because we're using the individual lag values for each point.
Mhm.
And so that kind of randomizes it a bit. If you had a fitted smooth lag curve, then this would just be a perfectly smooth curve.
Mhm. Well, it's definitely a correction that we should implement in WMPL and produce even more accurate trajectories and endpoints. Excellent. Thank you. Okay. Do we have any other questions or contributions at this point? I think we might have exhausted the topics. I think every year at this time when we approach it, it's the duration is roughly the same, which is very interesting. Maybe you can tell us something about human psychology. Or just our capacity for general state of tiredness after certain amount of meetings. Good. Well, I'm going to officially close our meeting for this year. It was we had some amazing talks this year, and if you didn't see the first session, try to make some time to watch it on YouTube. There are some very interesting talks there. And thank you all for coming. We will be in touch via email, and hopefully now we were able to put a face to a name, or I guess an email address. So thank you all so much for coming.
Excellent.
Thank you.
Cheers,
Thank
everyone.
you all. Thank everyone.
Thank you.
Good night.
See ya.
Good night, or have a good day.
Good to see everyone.
Thank you.
Take care.
Bye.
Happy fireball hunting.
Yep.
Yes.
Bye.